Get going. I'm John Sass from Ensembles Incorporated from Albany, New York, the USA, the neurological consulting firm. And I'll be the chair of the session. We'll have 4 speakers talking about public forecast providers and products. So we'll start out with Helmut Frank from PwC, looking at the seasonal forecasting products from PwC.
Thank you, and good morning. I first like to start with saying that actually I'm presenting for colleagues of mine. You see the name Andreas Paxian. He's also in the group, the same group as Christina Fröhlich, who gave a presentation last afternoon, last presentations. And so, but today's a holiday in Germany, and so he's going on vacation. He couldn't participate remotely. So then I'm trying to present you what DWE has as seasonal or climate products. That's page screen. Okay. So as was also mentioned yesterday 4 times, one of the very important things about these seasonal products is user communication, because as was pointed out, it's difficult to find out anything what can be used of it if you go for a few weeks. So that's therefore user communication is very important to educate the users what can be used, also to discuss how they might be able to use seasonal forecasts. And so there are different ways of interacting with the users. One is an annual workshop, which is going to be held next week in EWD. But it's in German, so it's focused on German users. But that's very important. Then there's a newsletter, also in German, and a monthly newsletter now in English. You see seasonal prediction of the GCFS, the German climate forecasting system, which Christina had presented. I think she's also writing it. This one, and then the status report for Germany. And then there's a lot of press inquiries, surveys, tweets, meetings. Andreas said there are lots of questions coming in. Probably there are not many people there, just a few people there. So and so clients are from different sectors: humanitarian aid, insurance, health sector, agriculture, forestry, naturally water management or water, hydrology, and the energy also, which we are here interested mainly. The main source of information could be the climate prediction website, which is also available in English now. It's German and an English version. It shows always the evaluation also. It shows presents the products at different time scales and weeks, months, years. So there's not a special section for seasonal forecast. It's just seasonal and climate predictions. So it goes from weeks to years. And there's different ways how the content of this website was developed together with the users. So they are always displaying the predictions and also information on the skill. There's the ensemble mean, and then there's probabilistic predictions, meaning terciles. As I said, different timescales, different regions, world, Europe, Germany, cities. That was a user requirement, or let's say the users wished it. Even so, we think that this might be too small scale, but yeah, users wanted it, so let's can try to see if somebody can get useful information. And it's the quantities right now. It's temperature, precipitation, the most popular ones. And as I said, there's always some information on skill. Try to present some information on skill because using these reference predictions, hindcast, which Christina had mentioned, and then there's the traffic light to indicate how well we trust the predictions. Saying if it's green, then we think the predictions are good, significantly better than just the climate reference. If it's yellow, then it's about equal, and red indicates that maybe we should rather take the climate instead of a prediction. And that's the way it's presented for Germany. Here you see Germany is divided just in 4 regions: north, south, west, and east. And then you see means, 3 monthly means. That's long scale. And this is for this summer, showing that we expect warmer than average summer. The color shows the sample mean, and then the traffic light shows if we think how reliable that forecast is, what we expect. So this is the first way how it's presented. Then therefore the different regions. It's also can show here the time series with the and also the numbers. That's also what the users always wanted. They also wanted numbers, tables, not just pictures. Here, similar for precipitation, now terciles. Here, I think it's interesting. The colors show the dominating tercile, which when you look here at this time series, you see here in the first 3 months, it's clearly that we expect wetter than normal. Whereas if you're here in May to July, here you would say, oh, you expect a dry season. But actually, when you look here, it's just a little bit more than the other one. So it's almost equal. So it doesn't make much difference. And again, the numbers. And this is, I think, Christina also already had this picture yesterday. Now this is now in more detail. That was made with these episodes, statistical downscaling, showing also now the expected prediction for temperature. And here the episodes makes the predictions on a 5 kilometer grid, and shown it is here on as these dots represent an area of 20 kilometers. So that's in more detail. So just not for the public. Here that's now from the global system for Europe, the sample mean, and the world here is precipitation in this case. So it's for Europe expected more or less almost normal. This presentation then shows in more detail the scale represented by the dots. So there's always additional explanation down at the bottom of the figures, so that the users can find out. All this data is online. For the global data, it's you can download it via Copernicus. That's just also where it's taken from. And this episode data or high resolution data there's a new portal, ECMWF, which will start next week with this user workshop in Germany. Then it should be open, and you can get it directly. And you should always follow the news, what's going on. Yesterday, I also learned that also news about our forecasting system. Somebody had also not caught up when we made some changes. So, yeah, as I said, try to, if something changes, it's also important to follow it. So there's some background information given, quite a bit of it. Videos are produced to make, to explain how to interpret these figures, the way it's presented. Yeah, it's in German. Yeah, but still videos. Then the FAQ, it's all on the side, on the website. So yeah, that's, as I said, and I got, as I said, I'm not in seasonal prediction. I'm in research department for the NWP. But for what I learned yesterday is still very important to get the users to learn how to use the information, because it's difficult to extract useful information from seasonal forecast. I've also learned. So now something to energy-related activities. There's a proposal on seasonal forecasting for energy. It's not funded yet. It's trying to for this high resolution seasonal forecast for radiation and 100-meter wind speed with this episode system, Germany, and using data from Copernicus. And then they also want to try to make final indices for teleconnections, as was mentioned yesterday, for the Dunkelflaute. That is no sun, no wind, and how probably this would happen, or how probable it is to occur. And then there should be also investigate different skills for different start months. You start at different times. And we hope that the project get funding and then might start this year. But I don't know. Other energy-related activities is natural information winter temperature. German authorities, especially last winter, it was naturally very interesting considering the gas market. If we expect a cool or cold or warm winter, which was very important. Then there is this newsletter, sub-seasonal and seasonal temperature forecast. And also here, sub-seasonal forecast. Here you see the forecast for different weeks, different months, and average them together. And here in the center, there you see different weeks, calendar more, that's different weeks. What do we expect for cold, normal, or warm weather? So that's the outlook for what might come sometimes. And that's also mainly now longer scale, so not seasonal anymore. Yeah, that's might expect in the future. So that's thank you. And with questions, I try to answer. I'm not an expert. Yes.
Regarding the traffic light stuff, how do you define the threshold? So I guess that for the red one, you imagine that you define like SPSS to below 0. It's red, but for the orange and for the green, how do you define these thresholds? And if it's the same for the different variables, maybe if you define a threshold for temperature, then in the specification everything will be maximum.
No, it's always comparing the sample forecast or how the model performed in the hindcasts. Well, there you can compare it with a reality because you know what happened. Yeah. And then you see if it was correct or if it was in the same tercile. I think they always compare the terciles if they are well correctly predicted.
Yeah. But if I correctly understand, it's a way to explain the skill of the prediction. Okay, so comparing, I guess that you use any statistic like SPSS or correlation or whatever. I mean, I was wondering how do you define this threshold between the red, the orange, and the green? Because it's that I think that it's a good approach to explain the quality of the forecast, but it's not easy to define.
It actually explains the quality of the hindcasts assuming that the forecasts have the same quality.
Yeah.
And from the ICAS where you compare, the ICAS, what really happened if they showed the correct terciles, but details I don't know. Yeah.
I was saying it might be in a documentation. I know
Yeah. Yeah, as I said, there's the FAQ.
Just a question about the users. You might have learned something from your equipment and sounds to me like quite thorough interaction with users. Do users really, in the absence of a forecast, use climatology? Do you ever ask users what they use if they don't have a forecast? I'm trying to think as a user, and I don't think I've used either the full chronological distribution. I might look at what happened last year, I might look for analogs based on something else. I wouldn't use chronology. I might be the only one. I'm just curious.
I don't know, but yeah, especially since there's the climate trend, so I don't know if they by themselves would say let's for example for temperature climatology and assume that it's a little bit warmer, but I don't know.
From my perspective, I know in agricultural users, they will use the best year they can remember and the worst year they can remember as a scenario for what to plan for.
So in a way, that's a climatology, but it's a climatology they can remember.
Climatology of experience is the problem.
Yeah, National Grid, my understanding is, it's not my team, but my understanding is that we use climatology. I don't know, I think we used to similar to that, now it's a little not.
Any other questions? I might have one on the probabilities. Are they from the raw NWP ensemble, the distribution of ensemble numbers, or is there some type of post-processing adjustment for reliability?
There, as far as I know, they are from the
NWP. So they aren't necessarily reliable in the sense that they match the actual distribution, right? The NWP might have a bias.
It's not NWP, the seasonal forecast.
I mean, seasonal forecasts are,
Yeah,
are based on NWP, right?
It's not the same model as our NWP.
Okay, so it's a separate.
As the system Christina had presented
Yes.
last evening.
Okay.
But it's these 50 members that they do for the forecast, and then
All right, thank you, comment. For our next presentation will be by Brookshaw from ECMWF, and the title is Long Range Predictions from Copernicus Climate Change.
My turn to provide some answers now, rather than just ask questions. Thank you for the invitation. I know that Christina really wanted us to come along and tell you more about Copernicus, and I might take a slightly different tack. I'm not going to show you things you can find for yourselves on the website very easily, but I want to make a couple of points, and please interrupt and ask questions because I would like this to be a bit of a dialogue. Firstly, I want to clarify I'm not talking about Nicolaus Copernicus, I'm talking about the European Union's program for space observations or for Earth observations more generally. It covers observations from space, but also in situ observations. And relatively recently, around 2014, it started to think about attaching some services to all this collection of observations. We ended up with 6 services, which are listed there. They're all operated in arrangement with institutions from Europe. So people bid to run these services, ECMWF did so, and ended up running 2 services, the Climate Change Service and the Atmospheric Monitoring Service. So when you hear about C3S or Copernicus Climate Change Service, this is what we're talking about. You'll find ECMWF outputs also in the Emergency Management Services portfolio, where we look after the operational predictions for hydrology and fire weather. What does C3S consist of? It's a variety of things, but many people think of it as a piece of technology called the climate data store. It's written as operational climate data store, around which things are built. So this is a place where you go to find data, not store in a sense of storage, store in a sense of shop, if you will. Although everything that Copernicus Climate Change Service and all the other services do is absolutely open and free for everybody to use as they please, as long as their purposes do not conflict with the interests of the European Union. That's the official line. So around this climate data store, we built a series of indicators and information systems and services for sectors, economic sectors. When I say we built, I mean we are constantly trying to build these, but it's mostly delivered via tools and applications so people can understand what's gone into the recipe, can modify it, and they can take and apply it for themselves. There's a variety of other things. Evaluation and quality control is an important feature. And again, we're still iterating as to how to best implement that. We do a lot of communication, we do training, we do user engagement. We extract information from a variety of things, primarily from monitoring activities, and promote it in political circles, economic circles, in newspapers. You might have seen us quoted in a variety of places. The most important thing here, I think, it's the user support. I mean, this is a service. You can actually raise a question and somebody will find where to pass it on to, and you will get an answer. And user support is also the mechanism through which we try to collect user requirements. If you wonder what's in this store, well, a variety of things. So observations and observation-based products, climate data records, essential climate variables, reanalysis. That's one thing ECMWF is known for. Yesterday you had ERA 5 mentioned that number of times. ERA 5 is just a number of products that have been developed since 2015 and continue to do so. So this is not really a coincidence. ECMWF has been doing reanalysis for a long time. The seasonal forecast products, data and graphics. There are forecasts or predictions on other timescales, and this is maybe a slightly older view of things, but we have extended into other timescales with predictions. And the distinguished predictions from climate model simulations. I might tell you in a minute why, but you probably know already. So we also offer access to the climate projections and climate model simulations for the past as well as I said before, sectoral climate impact indicators. This, by the way, I did put the URL there, that is the website, but you will have to be determined and patient to find your way around. So in a slide, I want to tell you what we have for seasonal predictions. We collect data from a number of, by collect, I mean, we have contracts with them, we support their activities, their operational activities, a number of centers from Europe. And after 2 or 3 years of doing this, other centers in the world who create global seasonal predictions have joined the game. So now we have 8 contributors, which are all listed there. So you recognize DWD, ECMWF, Met Office, Met France from Europe. Then we have the Canadian Environment and Climate Change Canada, NOAA's National Climate NCEP, sorry, Environmental Prediction, and the Japanese Met Agency. All this data is collected in as much of a uniform format as possible and is provided through an interface where people can interact with it in a sensible way, in a uniform way. We take the data, we put it in our archive, and then everything virtually looks the same. Data is a very high temporal resolution for a seasonal forecast, and apologies, yesterday I heard that somebody's downscaled ERA 5 to 5 minutes. This is not it. It's 6 hourly, that's pretty much as you can hope for a model that runs for about 215 days. We do some monthly statistics, but just basics, monthly mean, standard deviation, min and max. We also do some bias correction on the data, but very minimal. We just calculate the anomalies in a way I will explain in a minute. Data can be downloaded through a user interface form, nicely clicking on things, which also allow you to browse. So if you go to the form and you start to click on buttons, some gray out, which tell you that that particular combination is invalid. That's a useful way to approach the thing. Then you can automate your stuff and use the API to download things routinely. We have a set of tools and some programming shortcuts. We call it a toolbox, where you can use this, which you can use next to this data and create graphics that you can, graphical products, or indeed numerical products, which you can then download, whether you want to expose it to others or just in a private channel. We create some graphical products, but they are not definitive forecasts. So I don't think there is such a way as a universally valid and useful way to present the seasonal forecast data. We do it in a way in which producers like us have been doing it for a long time. We do it for few variables, so you're not going to find there everything you want. The next one on the list, in case you really like pictures, will be wind speed. But that's pretty much all you'll find there. We do, like everybody else, the ensemble mean, anomalies. We also do probabilities of categorical classifications of the forecast ensemble. So we look at probabilities of exceeding median, terciles, and quintiles. That is thresholds for which we know the climatological probability of occurrence. We create some indices for which we show time series, as well as probabilities of exceedance of percentiles again of this particular index or these particular indices. And for now, we just do sea surface temperature based indices in the Indian Ocean and the Pacific, as well as wind at 10 hectopascal and 60 knots. There are maps, you saw them earlier. I'm sure you have seen this kind of thing before. More novel when this was launched was the access to the data. So these were the seasonal forecast data sets that we had. It's a bit peculiar. It's split into two for each of the time scales, time frequencies. Now we have some ocean variables as well, which are not on this list. And as I said, there is a box, there is a form on which you can tick boxes and everything. That's the full set of variables from the surface set that I mentioned. We keep data separate for each originating center. You can see a few there. We keep the old systems for anybody who wants to compare things as they were in the past, but our main focus throughout is on the operational stuff. So effectively, currently we do evaluation and quality control by independent providers, and they look at the current operational system. Our priority is to give people things that they can use with a real-time control. As I said, once you go here, the navigation is much easier and more intuitive. There's a lot of documentation, and that's one thing I wanted to point out to you. So there's description of how things work, descriptions of the data available, description of the parameters, recommendations as to how to try to avoid failures in your request, known issues, and announcements. Announcements tends to be the most important thing, but I will focus on the description. So this is the list of models. I don't expect you to read all that, but when you do get a chance to look at that, you will see that there's a great diversity in a setup of these operational systems. So whilst we do pay and we do get people to, for example, cover the same period in the past with reforecast or hindcast, I call them both interchangeably, randomly, so apologies for that. We do not necessarily mandate the number of ensemble members they can run or the strategy they can adopt. We do want a minimum number of ensemble members because the conclusions you can draw, especially if you look at things over Europe, for example, or anywhere in the extratropics, you really do need large ensembles to understand what it is you're looking at and to distinguish between good and bad things. So, but we do not dictate the set up the operational schedule the way in which people do fit this into the bigger picture. Nobody does seasonal forecast exclusively, or very few centers do, if any. This is usually started off at the very least as a byproduct. So people in some places, ECMWF, one of them, did shorter range things, and then they tried to push the models forward, especially when they decided and they discovered that they can work with coupled models in which the atmosphere is coupled to an ocean. Others started from climate projection and started to initialize predictions to create seasonal outlooks. People do take our data and do much more interesting things with it than we do. So here are some examples. This is all we found on social media in the public domain. behind these things, there's a lot more stuff. I know that people do commercial examples. So here you have information on so World Climate Service. You probably know, you probably use the stuff. So I haven't got myself a pointer here on the right-hand side, which create bulletins for indicators that we don't calculate. All the data is there to calculate them, but we do not prepare them. There are people who just blog and do analysis every season and put words around them. There are people in the middle bottom picture which do skill assessment with a variety of scores. And there are people who look at more sophisticated things like tropical cyclone genesis using this data. At some point, users started to say, well, you have time projections, you have seasonal, what about the bit in between? Everybody heard about decadal predictions and wanted to know what they're about. So we did put out a small contract. We didn't want to start with an operational system. Decadal predictions, for those of you who've been exposed to them, are quite in their infancy. They are in research mode. By predictions here, I mean initialized model runs and ensembles of initialized model runs. We know that for a climate projection, you need to run the model, bring it to equilibrium, and run it for a number of years in the past, number of years in the future. A very expensive business, and you do it 2 or 3 or 4 or 5 times, and then you submit it to a model comparison exercise, and then 7 years later you probably do it again. Whereas in some cases we think that information can be got for more than 6 months into the future by just knowing the current state of the system. Primarily, for example, the heat content in the oceans, and not things at the surface, not things that we normally think of in the weather forecasting mode or slightly longer term mode. So what we wanted to do, given that CMIP, the Climate Model Intercomparison Project, already thought of collecting these decadal predictions, set up a protocol and signed up people to run them, and they collected them. We thought to set up an exercise in which we ask for case studies to see how to extract the information from this data. Decadal predictions are typically initialized every year, once a year. So the data is there. It's not exactly like an operational weather forecast, which you can have several times a day. So we had these offers for these particular projects. You can again find all this on the website. And very soon we'll also be able to find the data that these groups use. Each of the case studies, I should have said, was one particular modeling group. You can find the data that they use. This is what came out of it. So these are the prototypes. They create these clearly relatively static products because they only update them once a year. They do explain the performance of the model. They do explain the methodology, and they do show the forecast. You'll recognize potentially from the previous presentation, this is a case study that was done by DWD. This is a case for agriculture done by the Barcelona Supercomputing Center. There is one case for energy. It was about hydropower, and he was effectively just looking at precipitation. Again, I didn't want to go into it because I could talk about it for too long. But there is everything they put together, as well as the forecast issued. I think the latest one they have is in 2021, if I'm not mistaken. We did finish the first round of funding in Copernicus. We are now about to put out a call for the following one, and these products, if they have any users, will probably be updated because they are quite simple. So C3S has tried to promote some uses. We have contracted work to see how these things apply to water management, energy, health, forestry. The degree of success has been mixed. I mean, people have come up with very nice pictures and very nice interfaces, but the information content is not proven. Let me put it up. We are still working on an energy prototype. Well, the prototype has been prepared. Now we're working on the preparation of an operational service. I understand it's not yet published. We might hear about it later today. It's delivered by a group led by Alberto Troccolo. But when you start to think about how to use this data in applications, you come across common issues. It really doesn't matter what sector you're in. You need to worry about, everybody wants downscaling because they use models to describe the impacts. Models derived from observations or from shorter range forecasts, which come with very much more precision in terms of time evolution as well as spatial details. But we do know the models have biases, so you need to adjust that bias because it does come to hurt you. And I'll give you an example of that in a minute. The complexity of forecast system design is also an impediment. You saw there, I tried to illustrate with that slide about how complex and how diverse the ways in which people do their setup, their operational activities. You need to worry about what metrics to use for quality assessments. I remind you, these are probability forecasts, that ensembles, so looking at the mean probably doesn't tell you very much. The mean is the summary of the ensemble, which actually optimizes some of your error scores, but it doesn't actually, is not meant to represent necessarily one's realization for real world. Not to mention interpretation of use and use. So I'm not going to stop to go back to this. I did want to go back to the reminder that this is an ensemble. I think we've heard enough about ensemble. I'm not going to go to this. I will remind you, though, that the probability forecast has a variety of attributes, and the evaluation needs to look at those attributes separately. And for different users, for different uses, for different decisions, different attributes matter more. We heard the question about reliability. Reliability is important. You want to make sure you can believe those probabilities to be a realistic representation of what happened in the world. But reliability can be corrected by post-processing. It's the easiest thing to do. You also want your system to be able to discriminate between events and non-events, and that is not correctable by post-processing. There is perfect reliability in a full climatological distribution. If all you're interested in getting your probabilities right, issue probabilities, climatological probabilities, and that has perfect reliability. So there are features. People also scream all the time for sharpness. You want to distinguish between, as I said, between events and non-events. You don't want probabilities to be all in the middle, to be all 33% if you're looking at terciles. So there are balances to be struck. There are measures of, some people care about association. That's where you look at correlation. You want to know if one year to the next you go in the right direction. But other people, and I'm sure that in this room there are lots of people in that category, care about the amplitude, care about the error. Is the value you give me, or is the value that you invite me to take as my yes-no decision basis, is that actually correct or not? How far from the truth is it? We heard yesterday a question about, are we going to exceed 40 degrees again? Well, that's a question that you can ask from these things, but you evaluate your models in a much different way than you do in a standard sport. So the forecast bias, hopefully I've got another 5 minutes. Just a quick example, just so I make sure we're all on the same page. So these are highcasts for an index of sea surface temperature in the tropics, mean 3.4 as it happens. These are all the ensemble members created in the highcast period, 1993 to 2016. We plotted them here. You don't really know whether they're true or not, but we know that that's their mean. We go to the same period and plot the observations in black. Hopefully you can distinguish them. I should have probably done them year by year, but if you put them all there, the little thin lines, well, you probably can guess that they're a bit further up than the red lines. There's a lot of red lines at the bottom. Certainly the mean is higher than the mean of the model. And it's higher by a lot. It's about 1 degree, and that's a lot in sea surface temperatures in the tropics. So this is an important piece of information to bear in mind. The other thing you can look at here, this is a very nice, neat example. This distance between reality and the model world grows in time. And when you look at it, you think, well, why do I care? Well, this is my next forecast. This forecast, if I didn't know about the model climatology, ignore for a moment the red line, that is showing that all the trajectories in my current season will be, well, most of them will be below average. And I could do a lot worse than just believe that if that were actually correct. But that would lead me to believe, well, that's La Nina. This is the indicator in the ocean. But if you remember that these things are items in a model world, not in the real world, and you do relate them to the red line, you will see that they're all above average. So what I've done here is subtract the value of the red line from the green lines. And that is the opposite of La Nina. So it's that bad, it's that big, it's that important. It's not something you can ignore. And as you can see, there's a lot of spread. So we heard yesterday about very laborious methods of downscaling. You need to look at the model climatology. You need to do it, and you need to do it with large ensembles if you are interested in what happens in Europe. A same example here with The third side, so on the left, there's the model climatology. The third side, those pointed there. On the right, there's the observed climatology. It's possibly the same index, I can't remember. Here, it's not a very good example, but there are many, many examples where the distance between terciles differs as well. So normally we think, well, remove the mean, that's it. No, if you want to correct, you might want to correct for the fact that the distribution isn't fully, isn't robustly represented. And that's important because next time I do a forecast, if again I was to refer it to the observed climatology, well, more than half the ensemble members will be below average. But when I remember that I need to refer it to the model climatology, because those are elements in the model world, I come up with a different answer. Examples of biases. Here's one model. They grow fast. These are daily data. They grow fast. They grow differently at different times of year. These are two regions, by the way. On the left, there is the region in North America. On the right, there is the region in China. At different times of year, as you see in summer in North America, you have positive biases. The model just grows very quickly immediately after the initial conditions. It does so in China as well, but in China it also does the opposite in winter. That's another model, which is initialized more frequently. Then hence the more dense coverage with these values. But it is really a very complicated problem, and you need to worry about it. And you need to worry about it within your own application.
Can I
Because
ask a quick question about that graphic?
Yeah.
Is each of the squiggles is a reforecast determined bias for different initialization
Yeah.
throughout the year?
exactly, it's an average. In the top line is an average of 25.
Yeah.
Each line is an average of 25 realizations. In the bottom is 7. And it's an average over 23 years, 7 times 23 in each of those points for different initializations. You can see them here, I should have said, you can see them here with the observed climatology plotted next to it, but this is the difference between the two. So the second row of values. But you might think a weather forecast is safe. Not really, not in many cases. You at least need to diagnose this. Well, and then there's other errors. So that's got potential to do with the errors in a single model, and then models may have different errors, may have similar errors. So we tend to put information from models together to create combinations that may give us a better skill, than better handle on what's going to happen. I don't want to use specific words like skill in a way. Well, here's a very brief, very simple illustration of how a multi-model compares with its components. The top line is the multi-model. The bottom lines are the individual components of that combination. And the colors go from red to blue, better to worse. This is, I think it's Nino 3.4 in May, starting from May, yes, it is. And you can see it's not the same model that's worst everywhere. By worst, I mean least, has lowest correlation from this perspective. It's not always that the multi-model is better than the individual models. You can see a model here which at this lead time, and here I should have said these are the different lead times. So we have 6 months from each forecast, hence given that they're starting in May, June, July, August, September, October. So you see that you get some values in the individual model. The question is, if you only have one model, do you really think that using that by itself is going to give you always the right answer? Probably not. We've done correlations for maps of sea level pressure. You can peer at this at your pleasure and see that the combination is arguably better than the individual models, not all of them. So here you can see one of the models has positive values. I should say that stippling here means not significant. So the colors that make it stippling is what you need to look out for, and you better want red really than blue. So here you can see that in the multi-model, everything's stippled over Europe, but in one of them it's not. In others, it's really bad. So it's negative. So this is what we have to work with, to live with. Question is it hopeless or not? So this is a question that needs to be answered. Here I've just put some scores for combinations of models. We had historically 3 models to start with. Now we have more. I think I just put 7 of them there. I don't think you'll distinguish much by looking at those pictures. It's almost as if you throw a number of models in, you've already reached your goal of doing things better. It doesn't matter really how many you add. And in this map, I tried to make it even clearer by doing the difference between those. It's the rank overlay score, not the skill score. And here, the combination is better in the places where it's red. Again, doesn't matter which models which. Everybody has red and blue on the maps. Some maps have more red than blue. Right, I don't need to summarize this. I do have 2 more slides in which I wanted to tell you what ECMWF would be doing next for longer range timescales, but I have run out of time, so I don't know if you want to hear that as well. Anybody cares about, yes? Right, that means you want to.
Yeah.
I'll take it. Right, so you probably all used extended range predictions from ECMWF. Forecast range is 46 days. We heard about them yesterday enough. Current configuration, initializations every Monday and Thursday, 51 ensemble members. Model resolution about 18 kilometers for the first 15 days because the runs are in common with the medium range forecast, and then 36 kilometers. The users who really know their stuff have brought up the fact that this change in resolution does introduce some discontinuities which are undesirable. So the first thing that you should probably look for here is the fact that now the integrations will be run separately from the high resolution, and the resolution will be the same throughout. We haven't gone for the high resolution, we haven't gone for a lower resolution because we think that 18 kilometers still won't resolve everything. The model still isn't perfect. So we need to somehow grapple with the fact that the errors need to be quantified. The effect of the errors need to be quantified. So you'll notice the biggest change here is that the ensemble size has doubled and the frequency of initialization has increased significantly as well, more than double. So now every day, 101 ensemble members will be run with this slightly lower resolution. But if you look beyond day 15, this is not low resolution, it's the same resolution. There are details explained in the newsletter article. You can read more about it. You can see some examples as to why that makes a difference. But I think you don't need me to tell you that it's becoming unsustainable to downscale things one by one because the size of the ensemble is becoming huge.
Are you extending on ensemble size of the hindcast or just the forecast?
No, not the hindcast, just the forecast.
Can I ask a follow-up question? Yesterday, I was talking with a customer about this upgrade, and we talked about whether or not the increase in the number of ensemble members is materially important, given that the reforecasts are still 11 ensemble members.
Yes, because so what do you do with the estimate of skill? If you use the estimate of skill to calibrate your forecast, then you are not going to see huge benefits because your calibration is going to be a function of the ensemble size. It was the same before. The idea is that the real-time forecast, which knows about the initial conditions, which is more important to grab the signals there. So for the type of calibration that we do, which is just to remove the mean, 11 ensemble members, I can't remember how many there were, will remain the same. And the 20-year period that keeps shifting will remain the same because that is, that's not an. So maybe the way in which you calibrate might need to change. The seasonal, it's simpler. We do it much less frequently. We haven't yet pinned down the cycle. We think it's something that's going to be called cycle 49R2. Will come in 2022. The cycle will probably come towards the end of this year, but by the time everything is in place, the tests are done, the production of the reforecast is done, the implementation in operations is not expected to happen much before the end of 2022. The ocean model has changed. That's probably the most important change, apart from the cycles, but you're used to that kind of thing. The sea ice model has changed. And there the ensemble size is also increasing at least, well, by more than a factor of 2. On the 1st of the month, 101 ensemble members will be created, but there will be another initialization halfway through the month, and there the same number of ensemble members will be created. For those of you who are used to the 13-month range forecast, they will also be enhanced in a sense of initializing them every month. If you know now they're initialized every 4 months, so every 4 times a year, every 3 months. Next, they will be initialized every month. They'll go to 13 months. They will also be forecast longer than 13 months, but I didn't particularly think of wanting to speak about this here. But this is And for those who like hindcast to go as far back as possible, I can imagine people who want to do research and to see how things have changed over time. That would be of interest. It's likely things will go even before 1981. The operational hindcast period will remain 93 to present. There are some discontinuities in the observing system. I think the quality of the ocean conditions is not uniform. Altimeters, for example, came in around 1990s. So we, but because that's the world and our reanalysis goes all the way back, we want to understand how things are, how things work, how things change. We decided to invest some, this is just ECMWF separate endeavor, more for research purposes and trying to understand potentially with the model development. I didn't have time to put an example up, but we have started to see situations where the past may not be a good representation of the future. People try to talk about calibration, let's make spread, match, error, and all that sort of stuff. But we had a situation, if you want to look it up in November 2021, if you look at the predictions for ENSO, then you will see all models do roughly the same thing, but the observations do something completely different. This 3-year La Nina was not the third year where models really didn't want to do it. And that's not going to be corrected by calibration. So I'm sorry I didn't have the time to show you the slide, but I can try to dig it up and show you to the brain. Thank you.
Any other questions?
You briefly mentioned about operation capability. Can you elaborate more on that and what the challenges?
Yes, so money is one of the challenges. Well, we know that there are things that you can extract from the Gillian forecast, which are better and make your conclusion better than if you just use climate projections. But it's very much dependent on where you are. And let me just go back. Not a very efficient way to do it. We know that matters about where you are and what you want to look at, and frankly, what decision you are trying to make. Because if you, that's probably good enough. If it's a decision you can change every year, then something you can update every year might be useful. If it's a decision that you want to be lasting, maybe not. But in essence, if you're interested in the way in which things sequence themselves, this kind of information doesn't give you that for more than 2 or 3 years in advance, if you're lucky. If you're interested in averages, for example, people who want to invest in something, then maybe there is something to be gained. Initializations happen every year. The WMO has endorsed the lead center for the Gillian predictions, and they happen regardless. There's 4 global producing centers who have the obligation to do it once a year. So these things exist. What we're trying to do is to put them in people's way and to try and extract information and show people examples to extract information. This is a very, very telling exercise. We went through methodologies which seem very simple. So the one in the top left-hand corner, there's somebody here who can tell you more about it than me here, but there it's essentially understanding what drives the number of tropical cyclones. It is related to the heat in the subtropical polar gyre, the polar gyre, and effectively that is the information from the model that was used to try and derive it was a hybrid method. Take something from the model and use it to relate it to what happens in the North Atlantic basin. Roughly the same thing happened with energy. I believe that they took the large-scale atmospheric circulation, the NAO, and then they correlated that with the rain. Not surprising, that's all happening in Southern Europe, where there is a correlation with the NAO. The NAOs had scaled for a number of years into the future in a detailed prediction, and this is how that was done. Bottom left-hand corner, you heard of episodes several times. Took a domain of a Germany and tried with a very laborious and expensive method to find very high spatial resolution, 5-kilometer resolution rain over that particular river basin in Germany. The first forecast system, they found some significant values of skill for a particular period. The next forecast system, that disappeared. So the season was changed and the threshold was changed. So the question is, I'm going to take large-scale information from a particular domain. Why do I hope that that is good enough to tell me it's not just about detail, it's about detail that describes something driven by actual information, not just noise, not just random stuff. So for me, I learned more from that case studies than I learned from those that worked, because it is important. If you tell anybody, if I tell any of you here that the Gillian prediction is going to be useful for all of you, I would give you permission to boo me, because that's not true. There are people, there are decisions, there are activities for which the data predictions cannot offer anything, because you need to know when, how much, and that kind of thing, and that's not always possible. So this is the challenge. I think next round of funding might be more about technology and putting things in place, giving people the opportunity to use this data, giving examples of how to use this data, how to evaluate it. But we are not going to fund, initializations will continue to happen once a year. And but the climate prediction protocol and panel has decided they want to do shorter integrations, maybe 2 years, maybe 3 years, maybe 2.5 years, to see if sequencing of events can be pinned down with information potentially from something more than just ocean heat pump.
Okay, thank you very much. Very interesting study. We'll move on to our next presenter, Alberto from the Barcelona Supercomputer Center, and we'll be talking about climate services research lines related to energy at the Barcelona Supercomputer Center.
Okay, hello, thank you to everyone. So the idea of this presentation was to provide an overview of the different activities that we are doing in terms of climate services for energy, putting together different timescales from the sub-seasonal to the seasonal and decadal. Okay, so this work has been done in the last years for many people, so I listed here some of them. And at the end, I will also explain some of the current research lines that we have now. So first, short explanation for those that don't know who we are. So the Barcelona Supercomputing Center, it's the Spanish supercomputing facility. We have a cluster that everyone can ask for supercomputing resources. Also, industrial partners can ask for resources there. And beyond this, we have different research departments, and we are working in the Earth Science department. We are around 150 people working in air quality and climate, and I'm leading the Earth System Service Group. So the idea of this group is to take into account the background that we have in our department in terms of air quality and climate, to explore different user needs and adapt all the information and all the tools that we have to these specific needs. So in this presentation, we are going to talk about climate services for energy. So this is a figure from the ERC explaining the anomaly of wind in different regions in Europe. So this is something that now we are aware. So the climate variability, for instance, if we go to the Iberian Peninsula, where we have a lot of contribution from wind in the energy mix. We see that there are years that winds are higher than normal, but also other years that are lower than normal. So it's important to take this into account and to develop tools to better forecast these anomalies, and also to balance it with energy demand that mostly depends with temperature. So taking into account these needs, if we put together the different time scales. So in the energy sector, you are used to work with weather forecast up to 5, 10, 15 days maximum. Then also climate projections are there, and in the middle we have a set of different systems that are a bit in the middle between the weather, where you need a lot of efforts on the initialization, and climate projections, where it's more on the boundaries of the system. So sub-seasonal predictions, more or less up to 1 month. Then we have seasonal around up to 6 months, and then decadal up to 10 years. And in this figure, we have different applications for the energy sector. And what is important for me in this figure is that in the energy community, we are used to work like in silos. So the people that is working in sub-seasonal or in seasonal or decadal, there are different groups and different systems. Well, for the users, it's important to have all this together, because they have a need about to predict if this summer is going to be warmer than normal, and it's important to have all this information integrated from the forthcoming weeks, years, months, or even years. Okay, so yeah, now I'm going to show some examples of work that we have done on these different time scales, so from the seasonal, sub-seasonal, and also decadal. The first two case studies were done in the context of a project that was finished 2 years ago, the S2S project. And yeah, we start with this case study for seasonal. So in 2015, there was a significant wind drought in US, so that affected most of the areas with wind farms. Okay, so here we can see the anomaly of the first months of the first months of the year. And if we analyze the anomaly, so this figure, let me explain this figure because I will use it again later. So here in this black dot line, what we represent is the observations of in this case, of wind and daily values. And then these are the weekly average, okay, in black of the observations. And the blue region represents the climatology, okay, so what was normal for this region. And as we can see, during all this period, almost every week the winds were significantly below normal. And yeah, with what we wanted to do with this assessment, it was to first analyze if taking into account the forecasts that were available, if we were able to predict this, and then also to understand the reason behind this event. Okay, so if we go to the forecast, here is the forecast, the seasonal forecast, with a lead time of 1 month before, 2 months before, and 3 months before. As you know, we are working with Ensembles members. So these are the yellow dots, and we organize them in intersites. So yeah, 1 week before and 1 month before and 2 and 3 months before. So we already identified the most likely result was that the winds were going to be below normal, but these were the observations. So we were not able to predict this intensity, this event. So that's why you also include this information about the steel. So in the RPSS, we can see that that we had the skill for these regions to predict the whole distribution of the ensemble. But if we go to the Breyer-Skill scale, so for P10, what we can see is that the skill to predict this extreme, so this P10, yeah, it's low. And so this is, for instance, in this case, for this specific case study, so this was the point. So we were able to provide a forecast that was showing that most likely the winds were going to be below normal, but of course that it was not possible to predict the intensity of this event. What was important also for this, so at that time we were working together with an energy company, and for them, so this case study was critical in the US and affected many companies. And for them, it was also important not only to know if it was possible to predict, but to understand if it's something that was going to be repeated and the frequency of this. And on the news, there started to appear many news about that this wind drought was related to El Niño, and it's true. So if we see this map between the correlation of the El Niño index and wind, we can see that in North America, there is a strong correlation between a positive phase of El Niño and lower winds than normal. But we went a bit further, and what we did is that we ran different seasonal forecasts with different initializations. And in the end, we found out that there was in this area that it's highlighted here, there is an anomaly on the SST in the Pacific that promoted the convective movements. And in the end, it affected to these low winds in the US. So this, for instance, this work was published here in this presentation, in this paper. Okay, so again, to summarize this case study, so it's important also to understand not only if the forecasts are available to reproduce or to predict the anomaly, but also this offers tools to analyze if to understand the reasons that are behind these kind of events. Then, if we move forward to another case study, in this case, it's focused in Spain, summer in Spain, as you can imagine. If we have a heat wave, the electricity demand for cooling, it's higher than normal. And then at the same time, we have a wind drought. So this was the case in 2016 in September. So this was the anomaly for temperature, and and as you can see here, so the temperatures were higher than normal, and at the same time the winds were lower than normal. So this is an imbalance between renewable energy supply and electricity demand. And in this case, what we did, it was to analyze if the forecast for wind. In this case, the skills for wind were really low, and we were not able to properly predict this event. So as you can see here, winds were below normal, and the below normal probabilities were 26, 54, 3. So but for temperature, this was not the case. So for temperature, here we have also the information about the scale, and even 4 weeks in advance, it was feasible to see that the most likely percent was highlighting that maybe there was some anomalies, and not only for the most likely percent, also for the P90. So this is referring about the experience, and 2 weeks, and especially the week before, it was especially high. And then decadal predictions. So this is a work done in the context of UCP. It's another European project, and some highlights about decadal predictions. So as I said, so it provides forecasts between 1 and 10 years, and then we can analyze the scale and we can organize the forecast, synthesizing information for the forthcoming 5 years, for instance, or analyzing between year 2 and 5. And the main source of predictability of decadal predictions is the AMO, so the Atlantic multi-decadal oscillation. You can see here a representation of the signal, and it's a signal that takes several years. So again, so as similar to the discussions that we had in other presentations. So sometimes it's not only important to analyze the forecast for the specific variable, but also to be able to work with these teleconnections to improve the signal of the decadal. So in terms of subseasonal is the Madeleine-Julian oscillation, and here, for instance, is the Atlantic multi-decadal oscillation. In this case, we were working for wind. And so it was a challenge for us because there are different centers that are producing decadal predictions. Not all of them are operational, and not all of them provide sub-daily information for wind. And for this case study, it was important to analyze this sub-daily information. So we work with these systems. Some of them are run at BSC. And we did an exercise for North America, so for a specific location. Okay, and in the end, what we are able to provide is this kind of plots similar to the one that Anca was showing before for agriculture, where we organize the predictions interstyles. And we compare these predictions in the past with the observations, and we can also provide the forecast for the specific location. And then something that that we are starting to work now. So within the context of this project, it's called Aspect, that started in January. As I said, for the users, they have specific needs, and sometimes these boundaries between the systems, it's something that is not useful. And so there are two different approaches. So we can work with extended forecast, also with extended seasonal or with extended decadal, for instance. But also in this project, what we are doing is trying to combine those systems. Okay, so now I'm going to show two research lines that we are working on. So it's this work, it's not published yet, so it's still ongoing discussion. Okay, so on the first method, so now I'm going to focus on this seamless approach between seasonal and decadal. Okay, and the first method is based on working with the seasonal to analyze. To analyze the ensemble of the SST with the seasonal, and then analyze the members of the decadal predictions that are more aligned with this pattern of the SST. And we do this for every year, and then we define a subset of the decadal predictions that are more aligned with the SST. The idea of this method is that if we work with this SST, the whole simulation is more weighted for the different variables. Okay, and then we also have to take into account, for instance, that if we analyze the ability of the different systems, taking into account the SST. So if we put together all the members of the top 50 members or the worst 50 members, working at global scale, so for the SST at global scale, more or less we get the same results. While if we work in the area for the AMD, it seems that the top 30 members that are more aligned with the SST are the ones that are doing worse. While if we go to the El Niño regions, so it's we see that there is an improvement there is a potential improvement of the signal with these members, and then taking all these into account, we are able to generate these maps. Here it's the difference between all the ensembles compared to the top 3 ensemble members that are aligned with this SST in the Niño region. As I said, so these are preliminary results, and as you can see with this method, we are not able to improve anything in Europe. And mostly in all the regions that we improve are these regions with a higher correlation with the Niño region, most of them in the ocean, so it's not useful for the wind energy industry. But at least, it's a fair result. Then another method that we are exploring, instead of working with the SST, we are doing the same, but for the different variables. So we analyze the mean of any variable like temperature, precipitation, whatever, and for each specific location. And we do the same with the ensemble of the decadal, trying to constrain this using the top 30 members that are more aligned with this ensemble of the seasonal. We don't have still we don't have results for this method. We are working on this, so hopefully next year we will be able to present more information on this. And finally, I just wanted to highlight also the importance of working together in an interdisciplinary approach. So this was the platform that we developed in the context of S2S4E. So it was operationally providing sub-seasonal and seasonal predictions for a year. We were providing temperature, so all the essential variables, but also some specific indicators, like, for instance, the demand indicators were provided by the people from the reading that are here, or capacity factors for solar, wind, also hydro indicators done by SNHI. And the importance of this list for us, it was that not our aim was not to create a commercial platform, but to have a platform to really explore the forecast, because it's useful to work with case studies, but sometimes it's difficult to understand how we can use the skill in the prediction. So for instance, an effort that we do, it's in terms of design. So for instance, in this area where we don't have information, it's because we know that historically the skill was low. So we included a mask here. So for instance, this is the forecast for temperature for a specific day. I don't remember, 3 weeks in advance. The same for seasonal. So you see that the masks are changing. And also we did some user design analysis, and we changed the colors for variables like precipitation. And yeah, so the system is still available, but it's not updated. So it's we had the forecast for the last year of the project. And to finalize, instead of showing some conclusions, I wanted to highlight that we are putting many of our developments in different R packages that are open to the community. So for instance, we have been talking a lot about downscaling. So we are developing an R package to downscale seasonal forecast. So this is an example for South America. So it's already available, but we also have another R package for estimating some indicators, or in CS tools we have many functions to apply bias adjustment or calibration methods. And that's all. Thank you.
Have any questions?
Yeah, on the wind drought case studies, what was the impact? How big was the impact on the energy production, and then also did that correlate to higher or lower demands at the same time as well? I'm guessing on the Spanish one, it did.
But you mean from the one in the US or?
On both. I'm guessing the Spanish one did have much higher energy demands with high temperatures.
Yeah.
But on the US one.
On the US one, I remember it was critical because I'm not living there, but we were talking with some energy companies that they have also installation in US, and they were concerned. And in fact, thanks to this work, yesterday someone was showing a weather regime analysis in US. So we did something similar to this to analyze the weather regimes in US. So in the case of US, it was critical. In the case of Spain, it was not so critical because it was only for a week, and it was in September. So the temperature were similar to the climatology in July, August. So it was not a critical period, but it was significant.
Because I'm always interested in if the energy production is lower, but the demand is lower, then that report the exacerbates. I was interested in thanks.
For me, the critical point for this is that maybe now it's not critical because we have a backup with conventional power plants that in some hours in a day you can all the system running with petrol it's there. But in a context of the Green Deal with the decarbonization, then it can be more critical. If there is not a balance between different regions or different energy sources, it can have a huge impact. Okay.
Yes.
I just had a quick question on the similar stuff that you talked about close to the end. So you found that with subselecting the SSPs, there wasn't much improvement in the European region. So you said you were going forward to look at this RMSD method. What sort of variables were you looking at subselecting for to try and enhance that skill?
Now we are starting with temperature and precipitation because these are like the typical ones. But as I said, so we are starting. So this project started in January. We had some work before, but we are developing. So we are testing many different things to define like a strategy in this.
Yes.
A question about a combination of variables. I may not have paid sufficient attention, but I didn't see anything in which you can several variables together.
in Europe, many times low wind comes with a lot of sun. Is there interest in this? Have you done any studies that try to connect from modes of variability or large scale anomalies to a combination of variables which may, okay, if you just operate a wind farm, you have to care that there's sun, but for some decisions that might be
Yeah, we have putting some attention on this, but also we did this from the user's perspective. So in some sectors, there are some typical or some key indicators, or for instance, drought indicators, that is a combination of temperature, precipitation, or also evapotranspiration, wind. So we are working with some indicators that are putting together all these variables together. In the case of energy, yeah, for instance, I'm talking on behalf of the people from Reading, but they had they developed an energy indicator that was only for energy demand, but they also there was another indicator putting together also the wind.
Thank you. Now we'll have a joint presentation by Nicky and Gillian from the Met Office here in the UK. It'll be a remote presentation on the S2S products from the Met Office, and also some research on wind droughts.
Hi there. Do you want us to share our screen, to share the slides from here?
Yes, that would be.
I shall try and do that. Yeah, okay. Can you see those slides?
Yeah, great.
Great. Yeah, so hi, we're from the Met Office. We're going to talk about the seasonal forecasts that we produce for the UK. So first of all, I'm going to have talk you through the monthly and seasonal forecasts and the forecast briefing that we give over the winter months to the energy sector in the UK. And then after that, Gillian's going to talk about her work using the large ensembles we have and exploiting those to study potential wind droughts in the North Sea, which is of relevance to the energy sector. Okay, so I'm going to present this in context. So I thought it would be quite useful to have a look at the briefings that we prepare for the energy sector and have a look at the forecasts, generally what we do in the context of what we did last winter. So I'll go through the briefing that we gave in November for the DJF season. Basically go through the format of those slides, have a look at the North Atlantic Oscillation and why we focus so heavily on that. Go into the remote drivers of predictability, and we look at those, what they're doing for and its relevance to the North Atlantic Oscillation and our local climate. And then with the power of hindsight, we can actually have a look at how it all went over last winter and have a look at how well the forecasts did. I won't mention adding wind to the outlook, but just to say that this year was the first year that we did add wind to the outlook. So previously we'd only looked at temperature and rainfall, but now we look at wind as well. And that was thanks to a big effort from Julia Lockwood and Katie Hodge at the Met Office, who sort of led a cross-Met Office effort to get those in. And then, yeah, as I say, Gillian's going to take over at that point and have a look at her look at the wind droughts over the North Sea. So this is what the forecast was looking like in November for the December, January, February period. And we were looking at temperature here on the left, rainfall in the middle, and as I say, first time this season we were looking at wind speed. And the forecast overall was giving a near average temperature forecast, an increased risk of dry weather for the rainfall, and an increased risk of calm conditions. So I'll just run through these plots quickly because some of you might not have seen these before. We split the PDFs here. The dashed black line in the background represents the climatology, So that's the PDF of the observations over the recent period. The grey shaded PDF then represents what the forecast ensemble is predicting for that season. And how these line up with the coloured shaded regions in the background gives us an idea of the flavour of the forecast. So this blue region here is the lowest quintile of the observed distribution, and the red one here is the warmest quintile of the observed distribution. This middle one here is the middle 3 quintiles. So climatologically, we'd expect 20% of the observation of the climatological forecast, 20% of the ensemble members would be expected in this lowest quintile, and 20% in the highest, and 60% in this middle one. So when we have a look at the actual forecast distribution, we see 15% was in the coldest quintile and 20% in the mild quintile, with 65% in the middle quintile. So this is a slightly above average probability of being in the middle quintile and slightly less likely than in the cold quintile. I should say that forecasts now tend to be in the mild quintiles, have an increased likelihood of being in the mild quintile purely because of climate change. And we are now, and our observation period is 30 years in the past. So being a near average forecast is actually a slightly cold signal coming from the model. And when we present these to the energy sectors, it's nice to have a look at these tables. This places the forecast in the context of previous years. So we can see which years were mild and dry and wet, and being able to remember these previous years helps put the forecast in the context of what's occurred previously. So as I say, there was the greatest impact of, so it was a near average temperature forecast, but we were able to say that the greatest impacts from cold weather were early in the winter. And I'll go into that in a bit more detail on why we were able to say that. So we were also able to say that there was a reduced chance of wet conditions and reduced.
Two purpose che ti danno questo risultato.
Sorry, I couldn't quite hear that. Is it?
La trovi su.
So there was a reduced chance of impacts from heavy rainfall, and that we were more likely than not to experience dry conditions. We were also able to say that the risk from stormy conditions and high winds were lower than normal due to this higher concentration of ensemble members in this calm section quintile. Okay, so that was a look at the forecast. We also produce a monthly forecast, so we also had to look at the December forecast at that point. I'll focus on the seasonal one just in the interests of time. But the thing that we focus on from the forecasts is the North Atlantic Oscillation. This is the single biggest driver of our climate over the winter period. And the North Atlantic Oscillation is basically the long-term average mean sea level pressure anomaly pattern over the North Atlantic. So when it's in its positive phase, we have an increased low pressure anomaly over Iceland and an increased high pressure anomaly over the Azores region. And that drives an active storm track and sends all the low pressures continuously over the Atlantic towards us. And that then correlates to a climate of mild and wet conditions over the UK. And the other phase, the negative phase, we see a reduced low pressure anomaly over the Iceland region and a reduced high pressure anomaly. That reduces the pressure gradient over the North Atlantic storm track and gives us a weaker storm track. So we have fewer low pressure systems coming at us over the winter period, and that leads to a cold, dry type winter. And the reason that we believe the model is because the skill in this North Atlantic Oscillation is reasonably high. So when we look at our hindcasts, we see that the correlation of the predicted NAO coming from the model with observations is about 0.6. So although there's noise around the signal, we've got a predictable signal coming from the model. And the NAO is clearly linked to the UK energy sector, largely driven by the fact that it's related to the temperature that we experience over the winter. Okay, so what gives us confidence in our prediction of the NAO and therefore the UK climate over the winter? So we go through the list of remote teleconnections, and particularly I'll go through the ones that were important for the season just gone, the winter just gone. But we also look at other teleconnections in other seasons when there are different drivers. So this winter was fairly remarkable in that it was the third consecutive La Nina winter that we've had. And La Nina conditions tend to give a bit of an interesting response. So from work in previous studies, looking at the mean sea level pressure response in the Northern Hemisphere from La Nina winters, we see that the early winter response is this high pressure anomaly over the North Atlantic, and that tends to lead to a blocked conditions, more analogous to a negative NAO pattern. But later on in the winter, that then switches. So that previous plot I showed you was from November to December. Now in January to February, we see that this is a slightly different pattern. So this region here of the Aleutian has a high pressure anomaly, and that influences our mean sea level pressure anomaly more locally and leads to this high pressure anomaly over the low pressure anomaly, over the Iceland region, and leads to conditions that project more into a positive NAO. So we have this split driver of predictability, and that contributed to the fact that we were able to say that the risk of cold conditions was likely to be early on in the winter. Okay, so now we're after the fact, so we can have a look at what the forecast, how the forecast did. So this is the forecast as they were looking in November. So this is the ENSO observations in the black line, and then these red lines are what the forecast ensemble was doing throughout December. And we can update this observations line and see that although it was La Nina conditions, the ensemble was sort of over-egging the La Nina magnitude of the La Nina. But anyway, it was La Nina conditions at least. Okay, so the next teleconnection that was important at the time, particularly in that November before the DJF period, was the MJO. So we know from observations that when the MJO, the Matt-Julian oscillation, which is sort of, it gives us an idea of what convection is doing in the tropics. So this area of suppressed and enhanced convection travels around the tropics. And when it's in its phase 6-7, that tends to lead to negative NAO conditions over the UK. And we saw that the observations were leading to, were coming up here. And then when the line turns to a blue line is what the model was predicting. So it was in phase 6, and then the model was then predicting that to then advance into phase 7. And we know that that tends to lead to negative NAO conditions over the UK. So again, we can have a look at what the actual observations then did. So here we've got the red line was what the model was predicting, and indeed the observations did follow that quite closely, and it progressed into phase 7, and then the amplitude of the MJO decreased after that. So we could expect that to lead to negative NAO conditions. And that was another thing that was able to add to our confidence to say that the risk of cold weather early in the season was increased. The other thing that was active this year was the QBO, the quasi-biennial oscillation, and this is the measure of winds in the stratosphere over the equator. And this is a very slow-moving and predictable thing. It was in its westerly phase, and you just need to know that in its westerly phase, we tend to have stronger, a stronger polar vortex, particularly in early winter, and that tends to increase the likelihood of a positive NAO. This is in contrast to the previous drivers that we saw. So we always have to weigh up which ones we think are important, and the model can also help us with this, obviously. And then we can put the observations on here, and we see indeed it was westerly for the whole of the winter. Okay, so we can go back and have a look at this forecast and see how we did. So here's the PDFs that I showed before, and these are the probabilities in the quintiles for temperature, precipitation, and wind speed. And this is the verification of that. So we've got the observations from the recent period in the black crosses. So this is the climatology of what we can expect. The forecast that was issued in these blue crosses with the ensemble mean marked in the big blue circle. And then the blue star here is what was actually observed in that DJF period. So we see here that this was near average temperature conditions, well within the range of the ensemble. Perhaps a little warmer, but pretty near to average, and the signal wasn't big coming from the model. So that was good. The rainfall, let's see if I can get my pointer up, it's a bit annoying. The rainfall, again, was showing a dry signal coming from the model, and indeed it was a dry season over the DJF period. And the wind speed as well, we were predicting calmer conditions, and yeah, you can see that the wind speed here is in this lower quintile here. Okay, so the next, so yeah, I'll skip over that slide. So it's all very well having a look at these in the UK seasonal mean context, but I thought it would also be nice to have a look at something that's closer to what we actually felt, so the day-by-day variability throughout the season. It's not quite what we felt because it's still a UK mean, but it's a bit closer than looking at seasonal averages. So these are time series throughout the winter of temperature on the top, rainfall in the middle, and wind speed at the bottom. And the pink lines here just denote the different months. So on the left is December, middle January, and then February. And indeed, we see here this big cold anomaly early in December. So that when we said that there was a greater chance of impacts from cold weather in the early winter, that is indeed what we saw. And it was the La Nina combined with the MJO that was giving us the confidence in that signal. I think also in that period, when we were making the forecast at the end of November, we were also probably seeing this coming from the sort of more medium range forecasts, which we also look at when we make the forecasts. The precipitation was an interesting one throughout the season. So it was anomalously dry, as I said, and you can see from the verification plot over here. We had a very dry start to the season at the same time as we were having this cold spell. Then we had this wetter interlude at the end of December and beginning of January, and then a return to very dry conditions. And indeed, we had the driest February since 1993 and the 8th driest record in the UK mean on average, although there were some pretty dramatic records further south in the UK. And again, the wind speed, sorry, I should have said the black line, the black dash line represents the climatological average, but we can see that there's nothing dramatic happening in the wind speed. So it's around average. It came out calmer than average. But the notable thing is that we had no named storms coming from the UK. So there was one named storm, Otto, which happened on the 17th of February and had impacts across northern Scotland. However, we didn't name it, and there weren't any amber warnings related to this. This was named by the Danish Met Institute, I think. Yeah, so I think it's quite a rare winter that we haven't had any named storms. So the impacts from windy conditions were low this winter. Yeah, so that's all I have to say on the forecasts. Yeah, I'll hand over to Jill, and then if anybody's got any questions, we can cover those at the end.
Thanks, Nicky. Right, so I am taking a few minutes at the end of this presentation to describe some recent work. As I'm deviating from the climate prediction, but I'm going to talk about how we're using the ensembles hindcasts from these prediction systems in a way that they maybe weren't originally designed for, but which we can exploit to study extremes. And we have applied these methods to a number of extremes, mostly involving temperature and precipitation. But today I wanted to share with you some recent work we've been doing, applying this to wind droughts, so low wind episodes in the North Sea. The motivation for this, of course, is that in common with lots of European countries, the UK has ambitious targets for decarbonising the energy system. Wind is already a large component of the energy supply, and it's growing rapidly. We know that winds are variable, and so as the share in the energy mix increases, this could present a problem to the security of the supply. And an important question then is that, well, given that the observational record is relatively short, how well are we actually able to characterize wind variability and those low wind episodes? And so for that, we turn to this method, which we're calling unseen, unprecedented simulated extremes using ensembles. And the idea here is our opportunistic use of the initialized hindcast ensembles from the climate prediction systems to provide a large event set that better samples extremes and investigate their characteristics, the frequency, their magnitude, and also look at their dynamics as well. And in this study, we've used the hindcast ensembles from the decadal prediction system. The study domain that we've chosen is the North Sea, but it's a representative area rather than focusing on any particular groups of wind farms, because we wanted to keep things very generic at this stage. And also we've chosen the winter season because in that season the weather systems that give rise to some of the coldest temperatures are also marked by low winds. And so here we have our ensemble. Yeah, I should say that we're focusing also on the weekly mean wind speeds. So this represents an extended period, which, as far as I'm aware, cannot be managed through flexible demand or storage at the current time. So alternative supply is necessary. And the black dots show the reanalysis data. So ERA 5 data, we've got 13 data points or weeks per winter. And the grey dots are the model ensemble. We've chosen a wind drought threshold based on the 20th percentile of ERA 5 wind speeds. And because we've got this cube relationship between the wind speed and wind power, we would expect a large reduction in energy compared with a typical winter week during those wind drought episodes. So our grey dots turn blue before that, below that wind drought threshold. So now we've got this larger event set. We can start to mine it for information on the characteristics of wind drought, and we can see already that there are some simulated weeks where the wind speeds fall below that recorded through ERA 5. We can also look at the frequency and perhaps even more importantly, the duration of low wind episodes. So we're seeing that up to 5 weeks of wind drought is possible in a single winter, and that's set against 4 weeks in the reanalysis. Most of these wind drought events are single weeks, so interspersed with windier conditions, but we do get consecutive weeks of wind drought, and this is what is being represented in the figure there, that we have a maximum of two weeks recorded in ERA 5 so far, but the model is simulating wind droughts of longer duration, so with a 1 in 40 chance of 3 or more continuous weeks. And we do have a single worst case of 5 continuous weeks of wind drought. It's a rare event. We've only got one of these in the data set, but cases such as these could be useful in stress testing the resilience of the energy system. Finally, we looked at the dynamics of the most prolonged wind droughts and found an association with El Nino. So you can see that in the SST patterns in the tropical Pacific, and also this intensified Aleutian low. And indeed, we find that the chance of seeing these prolonged wind drought episodes increases, it approximately doubles during El Nino. I should say that the sample size, once we sub-selected the ensemble, is small, and it probably would benefit from more ensemble members or using different ensembles. But it is consistent with what we understand about the teleconnection between ENSO and the North Atlantic European sector. So just to summarise, I think that better information on characteristics of wind variability will be useful in planning a resilient energy system as that share, especially as that share of wind in the energy mix increases. So we've looked at various characteristics of the wind drought in this larger ensemble. Weeks with winds below the recorded minimum are possible, and we have the simulated chance of 3 or more continuous weeks of wind drought each winter, and our worst case of 5. As I said, there's this relationship with El Nino, and given that we have good predictability of ENSO, it could be worth monitoring and predicting the state of the tropical Pacific when assessing the risk of wind drought events in an upcoming winter. And I will leave it there, and I'll just put our summary of the different aspects of our presentation today. Thank you.
Thank you. Have any questions?
Oh yeah.
Can you hear me, Gillian?
We can't hear very well.
Yeah, no.
Any better now?
Yeah, slightly better.
Thank you very much for the presentation. I was going to ask Gillian a question about this method. I imagine that your conclusions about return periods for severe events would depend on the model you use for your exercise. Have you thought about how you address this in a multi-model setup?
Yeah, I mean, it's something that I think would be a good extension to the project, is to bring in other model ensembles, because yeah, it is going to be to some extent model dependent. What I wasn't able to show within the time available is that we do conduct some fidelity testing. So this is an evaluation of the model against our observations, or our whatever is representing our observations. And this we want to unseen as a method is kind of predicated on the idea that the observations can be treated as another member of the ensemble, if you like, so that they should be statistically consistent. And we conducted a series of fidelity tests for this model, and it passed the fidelity tests. I mean, it was biased high in terms of the wind speeds, but the other moments of the distribution were well captured by the model. So it did give us some confidence in being able to use this model in this region and in this season, which, you know, it's a method which doesn't necessarily, is not suitable for use everywhere that we would like to be able to use it. But given that the North Sea domain is a hotspot, it did seem like a useful application. But yes, so we do go on undergo this fidelity testing stage, but I agree some incorporation of other model ensembles would be a useful extension. Thanks.
Any other questions? Come on.
Hi. I just had a quick question about the use of the first winter of the decadal prediction system. I guess you could also use a seasonal prediction system there. I was wondering what the trade-offs of that might be.
Yeah, so in the Met Office context, the trade-offs are that we have a much shorter hindcast set from the seasonal prediction system. We could still use it certainly, but it's only from the decadal prediction system we've got right from 1960 to the present day. So we do have a better sample of these extremes. So that's why we've gone for it in this case, but there could be some well, on a really sort of mundane kind of reason, sometimes the seasonal prediction system has variables that are saved. They're not saved in the in the decadal system. So yeah, I mean, there's I suppose there's not sort of all of the variables we would like for the length of period of time we would like. They're not always available in these different systems. So it's just kind of, as you said, it's an opportunistic use of these ensembles. So it's just kind of finding the best fit to our question.
Any other questions? Are there any online?
No. Oh, I was just going to ask maybe an obvious question, but are there any plans to try and predict wind droughts in the seasonal forecast?
At the moment, we're just going to stick with the UK mean wind speed in the seasonal forecast. We haven't done any work to assess the predictability of low wind episodes within the season, and that's something that's unlikely to be particularly skillful. So I think, yeah, we'll stick with the UK mean wind speed for now.
Nothing online. Anybody else? No? Okay, well, thank you very much for that very interesting presentation. And I think we're at the end of the session now, so we'll have a break and be back here at 10:45.
No problem. We doing? Right. We're theoretically ready to go.
Welcome back, everyone. We're going to have another session of some of the companies that actually are offering some products. So we went from how do we actually do those predictions more to how can we apply those in real life. And the first speaker is Dutton from Prescient Weather.
You got it.
Who's going to talk about long-range forecast calibration.
Great. Well, thank you. Thank you for the invitation to speak. I will say I'm kind of honored to speak here. As a graduate student in the 90s, the University of Reading, and in particular, Dr. Hoskins came up like daily in my work. And so it's a great honor to be able to speak here on campus. And so just a brief bit of background. So the company is Prescient Weather. We have two products, and we made an attempt at climate change risk, but we were like 5 years too early, it turns out. But so we do primarily two things. Profit is it's a climate information service that integrates weather information into corn and soybean yield forecasts. It's used primarily by grain traders in Europe, the United States, and South America. And then the World Climate Service is a tool set that tries to integrate basically as much information as possible to enable a meteorologist to make a better long-range forecast. And so many of the issues that Anca talked about, we try to address in the tool. And then many of the information sources that have been talked about this morning, we generally try to integrate into the tool. So our customers are primarily meteorologists on energy trading desks. But there's two of note. One is the UN Food and Agriculture Organization Locust Monitoring Team uses the long-range preset forecast to try to get a sense for whether there's a risk for locust outbreaks in North Africa. And then interestingly, the Danish Meteorological Institute is using the World Climate Service to prepare their long-range forecast. And basically it's because it's just easier to get information through the tool than through public sources. So I'm probably going to cover some material that most people know, so I apologize if I do. But what we are trying to do in terms of the long-range forecast is we're trying to forecast deviations from the tercile distribution. So if we assume temperature in this case, could be wind, it could be solar, could be precip. We assume a tercile distribution, so equal 33%. And then when we make the forecast by post-processing the long-range forecast models, we're trying to forecast skews in that distribution. And so in this case, I've shown a 50% below normal probability forecast for temperatures, leaving 50% for normal and above normal. And once you've issued that forecast, if the observation then comes in weeks or months later and it turned out to be below normal temperatures, we call the forecast correct. And if the observation comes in and it's above normal or normal, we would term the forecast incorrect. And so I'm going to talk a little bit more about this later. So what do we actually use? So one of the questions in the material was, what do we actually do? So in the subseasonal time frame, we access the model data for CFS, the ECMWF, and NOAA's GEFS, right, which in November of 2021 is now run to 35 days forward. And we access the Japan Meteorological Agency. We calibrate them using the reforecast data. And in fact, like CFS is a difficult task because the CFS is a circa 2011 model. And so we're now 10 or 11 years past that date. So our reforecast, our calibration is actually based off the operational CFS data. Meanwhile, the ECMWF releases a reforecast in the run before the cycle of the live forecast. And so we download those reforecasts in real time and do a calibration on the fly. So ECMWF enables that, so model upgrades can happen without having to redo an entire complicated reforecast process. For us, it means we have to stay very on top of reforecast data and make sure we always have the latest reforecast. Then we also have a process where we combine the CFS, ECMWF, and the GEFS into a multi-model ensemble. And I don't have the statistics, but we can show that adding those three together creates a higher scaled model and better samples the uncertainty. And interestingly, for example, the JMA model doesn't add skill to the multi-model ensemble. So in this case, we don't include it, but we had a customer that asked us to include the JMA model. And so we go ahead and do that. In the seasonal time frame, we buy the ECMWF CS5 data, and so it's released on the 5th. And so again, we have a multi-model ECMWF CFS that we release on the 5th of every month. And then we wait expectantly until now the 10th of every month when we access the Copernicus climate model data. And so again, this is reforecast data and the real-time live data. And so we calibrate every individual model and we create a multi-model ensemble for that. So one of the statistics that I thought was interesting, just to sort of highlight the degree to which we're serious about this, Albert Soret showed that they have 3 petabytes of storage. So we wish we had that, but we do have 800 terabytes of storage to manage and process all of this data. That's roughly a third of what the Barcelona supercomputer has, which I thought that was pretty cool. But it's a lot of disks. And so the key then is that relative to renewable energy, so we are forecasting 2-meter air temperatures, 10-meter wind speed, and solar radiation. We would love to do 100-meter wind speeds, but unfortunately, the models generally make 10-meter wind speeds available. So in the subseasonal time frame, we're forecasting weekly averages or changes in the distribution of weekly averages. And in the seasonal time frame, it's the month and the seasonal averages. And so in the end, it's all a massive amount of data that we're processing. And we do research on a research system, but the real-time processing is all done in the cloud for product availability. So just to highlight what is calibration, what is interesting is as a private sector provider, most of my colleagues are not doing calibration. It is a complex process. It's not easy to do, and it requires a lot of data. which is one reason why it doesn't happen a lot. So the first process is correcting the model bias. So Anca showed great examples of correcting model biases. And you do that with the reforecast data. And then the second and more complicated process is adjusting the ensemble variance to reflect reality. So we happen to do that through a optimization process in which we're optimizing the cumulative ranked probability skill score. But the idea is you've got 20 years of ensemble forecast, reforecast history. You have 20 years of observations. You're basically trying to minimize an error function across that 20-year history. As I like to say, it ends up being coefficients, roughly speaking, and then you apply those coefficients to the real-time forecast as it gets released. And what you get out of it is a probability forecast. This is kind of interesting because the WMO reference on seasonal forecast suggests in yellow up top, reliability diagrams are recommended for the evaluation of seasonal forecasts. So we agree completely with that. And then interesting, so Stephen Rask, who is at least on Twitter, he's well known. He mentions that in academia, forecast skill reigns supreme. And so I find it interesting in reading models about verification. Reading papers about verifications with seasonal models. There's a lot of focus on root mean square error and mean average error and things like that. And those are always going to be low. And so you have to think about what else can you evaluate to see if there's going to be skill in the long range. So we think it's important to focus on reliability, meaning you forecast above normal with 60% chance, it should happen 60% of the time. We think it's important to consider what we would call understandable skill. So as a user, if my seasonal forecast has a root mean square error of 0.1 degrees, like I don't know what that means, but I do know that if I forecast a certain percentage and it's right a certain amount of time, that's usable information. And then we also want to make sure that all available sources of skill are used. So in our service customers, we write a monthly updated seasonal forecast report. And on one hand, I wish I wrote it, but on the other hand, I'm glad I don't. But so my two colleagues have written a report every month since 2009. So I've done a little math. It's 160 monthly seasonal reports in a row. So you learn some things when you do it that much. One of the things they've learned is that analog forecasting provides considerable skill when you combine the sources of information from the models themselves, and then sources of skill that may come from analogs. And in addition, they wrap in some statistical analysis. And so we as sort of technicians, and by we, I mean the scientists, we as technicians want to create an automated system where some model data gets pumped out, you use it in a system, and boom, you've got a more efficient process or something more profitable. But in the end, we have found that a seasonal forecast is best created by a human, because the human has to interpret multiple sources of information. And so that makes it difficult to integrate into an automated system. And so generally speaking, the ingestion of that forecast needs to be done by a human as well, that makes decisions based on the risk highlighted within that forecast. And so I mentioned analog. So this is just an example. So here's a chart, but it's already shown up this morning, thankfully. So this is the Copernicus models forecast from November of the Arctic Oscillation Index. And then interestingly enough, the black squares are statistically significant skill based on analysis of the reforecast data. But so there's a forecast here of what we would call a late winter positive AO index. And so the question is, what does that mean? So you can pick out years in the past that had a very strong positive Arctic oscillation during January, February, and March. And so I picked out the top 10 in this case, and you get a list of years, and then you can pop that list of years into an analog tool and see what the average of those years are. So the average impact on 100-meter wind speeds of a positive Arctic oscillation in January, February, and March is generally higher wind speeds across the northern tier of Europe and generally lower speeds across the southern tier of Europe. Technically speaking, this isn't an analog forecast, and that an analog forecast is that today there's a positive AO, and then you forecast what's going to happen in the future. This could be called a downscaling. So it's the climate models are forecasting positive AO, and then we downscale using past observations to try to get that signal. But this becomes like more tangible information potentially of what a positive Arctic oscillation might mean. I don't show it here, but you can actually go look at what happened during January, February, March, and there are, I will say, the images are not dissimilar. So it didn't, it's not a perfect forecast, but in fact, it was higher than normal wind speeds across much of the northern part of Europe. So this is a calibrated week 3. Is it wind speed? Yeah, wind speed forecast that was issued a couple of weeks ago. And the contours highlight the probability, in this case, of below normal probabilities. So this area is higher probabilities of below normal than the white, for example. And so I just want to highlight that because we're going to talk about reliability diagrams. So the title of the presentation is the benefits of calibration. And what we're looking at is the CFS, the GEFS, the ECMWF, and the JMA. And this is the calibrated the reliability diagram for 3-week 10-meter wind speed forecast. And we see the uncalibrated version, say when you're forecast 60%, it comes true 45% of the time. So that's an overconfident forecast. And when I am talking to users of our product, particularly energy traders, I tell them, most people are trading off of this information. You're trading off of that information. You should have an inherent advantage in understanding what's coming in the future. And we see though that then once you calibrate, you end up with a more reliable forecast. And so just very roughly, right? The benefits of calibration are to create a reliable forecast, so that the probability that you're forecasting an event occurs with the observations. And what that does is it makes those forecasts more usable because a user understands the risk of the potential outcome. Okay, so we're going to talk about briefly about usable forecast verification. So we've created a term that we call the tercile fraction correct, and it's pretty straightforward. I've created 4 hypothetical forecasts here: probability of below normal, probability of normal, probability of above normal. And then, so if we take a look at the dominant tercile, which is generally above normal forecast, then we go into the observations and we see that what ended up happening was 2 above a normal and a below normal. So 2 of these were correct, 2 were wrong because they fell into the dominant tercile. So the fraction correct is 0.5. So you can go into a reforecast or your operational forecast and calculate this statistic. And if you do it you can do it for regions and time and lead times, and you end up with the tercile fraction correct statistic. I love this graphic. It's a little complicated, but so we have the tercile fraction correct on the y-axis, and then we have the probability of the forecast here. And so what we see is that as the probability increases, your fraction correct is likely going to increase. And then in fact, we also see that the black line is the calibrated solution and the green line is the uncalibrated solution. Someone's going to ask, why is it jagged? And it's jagged because there's only 11 ensemble members in the reforecast. And you end up with what you end up with that. So then I also like to say that the penalty you pay for calibration is that there's increasingly less often a high probability forecast. So we see, like for example, 75% chance of a week 3 above or below normal forecast is only issued 1 or 2% of the time. So and that's the penalty, which is you want high probability forecast week 3 because it means you can make a decision from it, but it just doesn't happen that often. And so again, the colors here highlight the benefits of calibration. So what that sets up then is what in the subseasonal time frame is called a forecast of opportunity. So if you are lucky enough to review a forecast that materially impacts you, and it's, let's say, 3 weeks out or a month out or something like that, and it's high probability, you know that high probability is unlikely to happen again anytime soon. And if there's a material impact to your your organization or your business. It's a forecast of opportunity, because knowing the probabilities are high, it's likely to be correct. And then knowing that this doesn't come along very often, you know it's an opportunity to make a decision that could materially impact your business. And so the key is that the probabilities within the forecast allow you to evaluate risk. And so you might be well, let's say you're a wind energy provider, and the week 3 forecast shows a wind drought over Germany with a certain percentage. You know what the risk is of that wind drought occurring based on a reliable forecast. And then, so reliability diagrams can also be created for probabilistic forecasts. So in this case, this is, I should say, from the seasonal model. So this is the climate forecast system. We have an uncalibrated forecast of temperatures on the right-hand side and calibrated on the right. So calibration is awesome. It's a great tool, but the challenge is that it's difficult to take a weekly average probability and convert it into a power forecast. And so we have done projects where end users have said, we want seasonal power forecasts. And we honestly don't know what the right solution is yet at this time, because you can't just take a weekly average anomaly or sorry, a monthly average anomaly or a probability and turn it into a probability, into an actual power forecast. And so what I will do is point out a couple of solutions that we've ended up working with to try to enable. So one solution was that we had some station data from the customer. So the tall tower station data from the customer. We had it over, let's say, 4 or 5 years. And then within the reforecast data, we can calculate the bias of the model against the wind observation. And then when the real-time data gets released, we can take daily resolution wind speed, which has absolutely no skill whatsoever in the long range, but we can bias correct that wind speed, and they get something that allows them to make a decision and say they're using seasonal data to create a forecast. And so that worked. They gave us some statistics. They gave us some verification statistics, and to be honest, we didn't believe them. Like, they were way too good. And if they were that good, I wouldn't be standing here right now. I'd be on the beach somewhere. So we're not sure what happened there. So that's one possible solution, is to just directly bias correct the model to create that local sensitivity to wind speed. This one is more creative, which I thought, again, this is a customer of ours. They're a major wind power provider in the United States. They've got a fairly substantial number of wind power generation sites. And at each site, they have a tall tower. And they found the relationship between their tall tower and the reanalysis data, the ERA5 reanalysis data. Given a few years of data, they can apply that relationship and create a 70-year history of hourly wind speed. Given that hourly wind speed, they can create a 70-year history of wind power production for each of their sites. And so they get a wind power climatology generated by the ERA5 data, but corrected to their wind speed. So then they get our seasonal forecast. We have images like this, where we're calling out the analog years that we're using to create an analysis. And the thing that I learned that again, I was pretty amazed by this, they take those analog years and they pull their analog power generation years from their database. And then having done that, they get a distribution of power generation based on this analog forecast. So we didn't coach them on this. They kind of did it on their own, but it was one way that they're able to take a seasonal analysis of some kind and generate a power forecast out of it. And so I think that one of the challenges is this idea that to gain skill out of the models, you have to do some form of calibration. It might just be a bias correction. It might be a transition to probability, but then converting it into power because of the nonlinearity of wind to power creates a problem. And so that's one solution. Hopefully there's many more. So just briefly, I'll just summarize. The real benefit of calibration from my perspective is that because the likelihood of being correct is directly proportional to the probability. It means if you're a forecaster using this information, your confidence in that forecast is directly proportional to the probability. And so if the map is white, it means climatology forecast. There's no information to make a decision. If it's 60% or 70%, there's a high probability. There's a high chance that that forecast is going to be correct. And that's the primary benefit of calibration. The challenge, though, is how do you apply it in power generation? And I have yet to find or see a solution that does that directly. Cool. That's it. Thank you.
So I guess the benefit of calibration here specifically for having your confidence in your forecast. And then you mentioned that this will enable the energy trader to have a financial benefit. In working with your clients, have you been able to tease out that financial benefit?
The problem with working in the trading environment is no one tells you what their strategy is. Meaning they're very hesitant to tell you what they're doing because of how they make money. That being said,
Yes, no, like, yes, it is giving us a financial benefit versus no, we haven't seen it.
the answer is yes, yeah. And so what we hear is you end up hearing about individual trades that the decision was made on using this information that went in their direction. And so, like just last week, I heard of an $8 million trade that was influenced by the decision they made.
That's also anecdotal, potentially.
It's potentially anecdotal, yeah. Yeah.
I wanted to make a couple of comments and ask you a couple of questions.
Sure.
Firstly, the publication of these 5 data, you know, that is available on the 6th of the month now. You know, the Copernicus
no.
The others are on the 10th, but it's in the
Okay, I did not know that.
Thanks on the 6th. The other thing is the more recent cycles have already included 100-meter winds in the list of diagnostics. You don't get this sub-seasonal.
But the rest don't, right? The rest of the Copernicus?
Not yet, but the next updates, we have spoken about this, and the next analysis will happen.
Right.
So that's, but I think your next cycle sub-seasonal will have that.
Yeah, so the challenge, so I will say, I may not know it, I'm sure my colleague Richard does know this. But the challenge is we don't want to continually iterate the product based on like small tweaks. So when the whole Copernicus system goes to 100-meter wind, we will as well.
You might want to use it to verify if your extrapolation because it's the same as that model.
Yeah.
I really like your comment about verification of more information and meaning to users. I was wondering in that context, and we're working on that, we're just now useful. I liked your fraction of decile fraction correct. I wondered if you care though about when things are wrong, things don't fall in the right decile, care about how wrong they are. Because that score doesn't penalize differently if you miss by 1 or by 2 categories. So there are ordinal category scores. I remember working with such things. So yeah, we are working on that. But the last question maybe, you did say at the end that climatological probabilities don't no information to base your decision. Is that how the industry sees it? Because from my side of the fence, I used to think that tells you something about the state of the climate, assuming you've done all the calibration twice.
Yeah, I guess I am coming from that statement is made from my customer's viewpoint, where if you're a meteorologist on an energy trading desk and you're being asked what's the weather going to be in 3 weeks, and you have to say something. A white map means something. It just means there's no information in the models to be able to call that. Or it actually means in the calibration process, there wasn't skill. And so when you have no skill, you forecast climatology. The problem is you don't know which one it is.
It could also mean that the weather isn't predictable.
That's what I'm saying, yeah.
Yes, so
the point I'm saying is a customer, a meteorologist might be expected to make a call in 3 weeks and they're staring at a white map. And what do? So what we tell them to do is go look at analogs and see if there's something in the analogs. But from the
shorter range forecast.
Yeah.
Thank you.
Sure. Anything else? Yeah.
Just wanted to quickly ask about whether you consider different schemes for calibration.
So again, I'm sure that we have, but this actually was the calibration scheme that we ended up with. It was a major multi-year effort to make it work the way that we wanted to work. We do stuff like we convert nonlinear variables like wind and present into linear, sorry, into normal, calibrate, denormalize, and that was complicated in process. So to be honest, now that we've got something that works, like we're gonna ride it as long as we can.
Well, just the reason I ask is that calibration is a little bit from the eye as a whole. Many meteorologists quite sensibly would want to calibrate to minimize errors over a long time series of data.
Yeah.
And that's good in the round, but from a kind of good operator point of view, really interested in extreme cases. So perhaps another good way of calibrating would be to calibrate on those extreme cases to make sure they're forecasted well. And you know, we have maybe a different forecasting system for getting the weather quite generally, and perhaps have a specific one for these extreme cases.
So we have let's say explored the possibility of calibration for extreme events. It's a very difficult thing to do, and in fact, the release of the 100-member ensemble is going to make it much more realistic to be able to pick out extremes out of the ensemble. Did you have a question?
Yeah, I just like how the whole thing is like very much like what is achievable. Like, can we actually gain? Maybe the like statistics don't perfectly work out, but you make something reasonable and meaningful to be used. So that was definitely nice. Also the wind, that wind problem you showed, that's exactly the problem I've got at the moment. Trying to do that in going back and getting 70 years worth of data and plugging that into the model, it works. It can work, but it's kind of laborious having all of that data. If you haven't got the capacity for that, that's tricky. So still trying to work out that one. The question I had was just to understand the process. You lost it at one point. The analogs, is that saying that you've taken some historical seasonal pattern and then the analog there is then the half-hourly or hourly data? You then sample that from the last 70 years. So that these all look similar.
Well, no, it's just the analog identifies 10 years, 10 individual years, and they're just pulling those years out of the database and then using that as an estimate of their conversion to power.
Okay.
But then understanding the range of possibilities.
Good. Okay. Brilliant. Thanks.
Great. Thank you. Oh, yeah.
On the analogs, you're using the last 70 years.
Yeah.
As I see it as a meteorologist, there is a problem with the old analog years that they don't have the climate change within them. So I have some kind of difficulty in trusting the old analog. How should I address that?
So in our tool, you select some stuff and a list of years pops in. That list of years is editable. And what our customers tell us they're doing is they're eliminating everything before 2000, and they're just using the last 25 years. And it's for temperature, it's absolutely true. And I will say, I mentioned Richard and Jeremy use analogs. They also are telling me seasonal forecasting is becoming more hard because the analogs aren't as valid anymore as they used to be. Cool. Thank you.
Well, there's one question from the chat.
Oh, yeah.
And that's from Gerard Castro Castillo. Which kind of forecast calibration procedures did you find the most useful when it comes to removing model bias and correcting ensemble spread? Do you use those forecasts calibrated versions for further statistical downscaling, such as analogs?
So the answer to that direct question is no, we do not use it for further downscaling. And I'll just say, like, again, just high level, the role of the private sector in this business is to answer very specific questions for very specific end users, and our end users don't require downscaling, and so we don't do it. So hopefully that answers the question.
Yeah, it should be.
Okay, thank you.
Thanks a lot. Then the next speaker is Alberto Bosch from Vortex, and I see you're on our screen already. Very good. Please take it away. We can't hear you. We still can't hear you. But that's Can someone else say something to see whether that's on our end or on your end, please?
Hi, can you hear me?
Yes. Okay, so Albert, that must be on your end then. No, nothing.
Try to change the audio settings. Maybe you haven't correctly selected the device.
Are you familiar with Zoom? There's the little button at the lower left end called mute, and from that one you have the little triangle that can fold out.
Now it's good. Now
yeah, it's good.
Okay. Sorry about that. First of all, thank you for the invitation to talk about our product, about the seasonal forecast from Vortex. I'm Alberto Bosch, and I will present you the seasonal wind speed anomaly forecast. Okay, so we at Vortex, we are wind data providers. We use the WRF model and we provide different wind data for the different wind farm development. We provide from the low resolution wind speed maps to high resolution wind speed maps from hourly time series to 10 minutes time series. Okay, this is all about information about Ensembles. We use several different reanalyses from Era 5 to CFSR or MERA2. And we also provide some forecast. We have a company who provides the short-term forecast, which is Sirocco. It's a partner of us. We at Vortex provide the seasonal forecasting, which is the tool that I'm going to present you. And we also have a spin-off from Vortex, which is Climate Scale, which provides decadal forecasting and climate projections. Okay, we at Vortex, we are able to provide 30 years hourly time series in all the positions in the world. So we use that time series as a ground truth for this new tool of the Vortex seasonal. So we use, first of all, we launch a Vortex time series in a specific location, and then we also have the seasonal models from the Copernicus. We use the 7 different models provided by Copernicus, and then we cross-check how has all the models performed during the coinciding period with the Vortex time series. We do the monthly averages, we do the wind speed monthly averages, and then we cross-check all this information using machine learning techniques with some of our own metrics, some of the typical metrics to analyze which is the best model which has performed for that specific prediction. So at the end, we are able to choose to mix or to produce a new forecast for a specific month. Okay, so for that information, we have developed a tool. It's a completely tool where we have global and local information, and where we have also historical and forecast information. Okay, so first of all, we deliver, which is available from Copernicus. It is the Era 5 wind speed anomalies for the last 4 years. we have a global information for that. So that there is a map with the anomaly plotted there with the red and blue typical colors. And we deliver there the information for the last 4 years. And each month we are updating the data for the last month wind speed anomaly. You can check here, there is the April monthly wind speed anomaly over the period 1991 to 2020. And you can check the same information for quarters, semesters, and the full year for the last 4 years. In a global way, we also deliver here the information that we download from the Copernicus, which is the 7 different models from the ECMWF, Met Office, and the DENSET, the German model, the Meteo French model, the Italian model, and the Japanese as well. And we deliver here the next 6 month wind speed anomalies, next 3 months altogether averaged, and next 6 months altogether. So this is a free information that we use to fit our system that we put here for our customers to analyze what has happened during the last year, during the last month, or what are all the models saying for all the globe. Okay, so focus on the site-specific forecast. We can deliver the information, and we use the Vortex model for that information. So if we look for one single point information, we have the same information as for the global maps. First, we have climatology. We have the 13 years Vortex time series with the monthly averages. So we deliver that information here. You can have the climatology for that point, and the monthly wind averages, the full year mean averages, maximum, minimum, standard deviation of all the climatic period. And we also deliver monthly information for all these year by year. So you can check from the last year, or you can check for 30 years ago. You can check it in wind speed anomalies, or you also can check with a wind speed value. So each month we update this information. Okay, this is no forecasting, this is only hindcast, but we want to deliver also this kind of information. And then we deliver each month, we deliver the next 6 month monthly prediction. Okay, for that prediction is where we use the Vortex model, which is, I remember you that from the last the flow chart, which is the cross-checking of the wind speed Vortex time series for the last 30 years with the performance of all the models from Copernicus. Then we cross-check this information, and we choose, we mix, we do a prediction for the next month. This is the last month prediction from May to October. And here we have the values. For example, for May, in that place, it's minus 7% wind speed anomaly over the climate of reference. And we have this information for the next 6 months. We also have here a square color, which is kind of a predictability. It's our way to show the skill of that information. This skill is historical predictability. This is how the performance of choosing the Vortex model has performed during the last 30 years, during the coincidence period with the seasonal models and the Vortex time series. Okay, so we give here kind of a skill information. We told that historical predictability, and we have which it is always better than climatology. We have built this tool to be better than climatology and to be better than using one single model. So the predictability is lower when it's close to use the climatology. The predictability is normal when it's slightly better than using the climatology, and the high predictability is when during the last 30 years we were better than using the climatology. Okay, Here we do not we present a deterministic forecast, but we know that the seasonal forecasts are not a deterministic forecast. So we also present a distribution of the ensembles for that specific prediction. We use the probability distribution of the ensembles, and we also provide the tercile probability of each tercile. For example, in this image, we deliver this -7% wind speed anomaly, but we also deliver the tercile probability, 76% for the low tercile, 15% for the middle tercile, and 7% for the upper tercile. Okay, this is a extra information that some of our customers also want, the probabilistic information. Some of others, they only want the number. We know the number is kind of a reduction of the information, but we deliver that information as well. We also reach to the next 12 months. Then we don't use the seasonal models from Copernicus, which only reach to 6 months ahead. So we want to deliver to 12 months ahead because most of our customers are from the wind industry. So they usually have the annual budget production. So they need to know the full next year how it's going to be. So we also provide this information. What we use for providing the information from the month 7 to the month 11 is statistical methodologies. Okay, then we use only statistical methodologies for the month 12 to the month 7 to the month 12. It means the Q3, the Q4, and the S2, and for the full year. And this is all the information that we provide. Information for the next 6 months, month by month, and information for the next 12 months in a quarter, semester, and annual basis. We also provide the possibility to check what has said all the other models in that specific place. So we deliver for the next 6 months the information for all the models. So you don't need to go to the map and check which has the model saved for that region. You can look at here which has saved all the models for that specific lot location. You can choose whatever you want, and you can look which is the different information that all the models provide. And you can check also which is the information that Vortex gives to you. Okay. So all this information at the end is summarized in a Vortex tendency table. This is a table where you can find the prediction for one place from the November on 2021 till this May prediction. You can also check that the anomaly. The anomaly is what the ground truth, the Vortex time series at 3 kilometer resolution monthly wind speed anomaly says. Okay, this is for us, this is the ground truth. So we check how has performed this month. Then we have for each row, we have the 6 different predictions done from 6 months ahead to the same month, and the wind speed anomaly for that specific month. This table is validated in the same tool, and you can check which is the performance of this model, of this table, of all the predictions that we choose for that specific place. For doing that, we use 4 different metrics: the bias, the mean absolute error, and then we use the improvement and the trending. This is two important metrics for us. The improvement is how using Vortex model is better than using climatology. How many times in percentage? And this is the improvement metric. And the trending is not only that we are better than climatology, is that we have catch the trending of that specific prediction, if it's going to be positive anomaly or negative anomaly. Our customers are from wind industry, so the main concern is if they're going to have more wind or less wind. So that's an important metric for us. And it's the main metrics that we use when we check check all the seasonal models with the Vortex time series, which has performed better. These are the 2 metrics that is more important for us. For the validation for the table before, you have here the metrics. it is a very good place. It is a very correlated region with the seasonal models, and this is a very good metrics. Okay, you have different metrics for the 1 month ahead prediction to the 6 month ahead prediction, and you also have the average for all the 6 month ahead prediction, and we can reach near the 79% about the trending, and near the 69% of improvement over climatology. Okay, this validation is also made for the quarters prediction and for the semester prediction, and here you have the same metrics as well, and more or less the numbers are in the same way. If you use a quarter or semester, sometimes it's better than using only monthly predictions. Okay, this validation, these metrics are for one specific place, but we also have validated this information all around the globe. We have used sites on wind industry regions of interest. So these are our customers are in that places. So that's the places that we have chosen to validate this tool. We have chosen 50 locations around the wind industry regions, and we have average metrics around that. We have trending over 60% and improve around 60%, a little bit less. It is using all these sites in all these different regions for all the predictions from the month 1 to the month 6. We can reach, as you have seen in the validation before for one specific site, a very higher metrics, but we also have some places that we have lower metrics. At the end, in a global validation, we have a numbers like that. Okay, this is all that I want to present you, and I'm up to you for any questions. Thank you.
Thanks a lot. Any questions here in the room, Anca?
So I was curious about your technique of picking a best model, and I'm trying to work out how that's done. You say every time you have a new forecast, you re-evaluate your assessment of what's the best model, and then use that for the next forecast. How frequently does your best model change?
It changes for each prediction and for each month in advance. So we, at the end, we mix all this information. We don't use a continuous only one single model for one specific point. We use one different model for each month and which prediction in advance for that month. So at the end, and for each point, yeah.
So that's a bit odd, because if a model was really better, then you wouldn't need to change it every time. It sounds to me like this is a borderline judgment as to which is better. If every time you do the forecast, at the very least, next time, the same time next year, you should find that the same model is the best. So, and also using different models for different locations, unless the locations are meaningful to your user, might break down the sort of coherence of the whole system. That was my immediate reaction, but yeah, you probably analyzed all this.
Yeah, that's true. But the main thing of using this way of using different models for different prediction and different predictions in advance for the same month, it was that we noticed that using only one model, we had less skill than using all the models. So the way that we use that is to step the two first steps that we want for that product. Be better than climatology and be better than using only one single model. So the mixture of all the models is better than using only one for that specific prediction. That's the reason.
Okay, thank you.
You're welcome.
Maybe I'm having a question to. Yeah,
so you can pick that.
Maybe I'm having a question to that one. In one of the earlier slides, you showed this several years of 6-month predictions and the anomalies. And I would expect that you keep some traces, but it seems that, yeah, that one. It seems that there's really not much consistency between individual runs. So you would think that this is a feature that goes somewhat diagonal in here, where you have red streaks and then blue streaks. But it seems that the seasonal prediction changes from month to month. Can you elaborate a bit on that?
Yeah, that changes of the seasonal prediction month by month. It is here because our method, but it is the same changes using only one single model. If you have one single model, you kind of have in a one single point. Remember that it is for one single point. If you want to analyze a big area, that's different. Okay, we also have a tool for that. We have a kind of a tool to average different points in the same region. Okay, but if you look for one specific point, the wind speed anomaly predictions for one single model, it also changes as in our model.
Okay, thanks. Go, David.
Thanks. I just want to follow up a bit on the verification stuff as well, because I mean, some of the results sound to be incredible. That you know, getting predictive skill on monthly averages 6 months ahead sounds like a fantastic result if it's a genuine result there. But I guess the thing I would put it on your improvement score. I think on one of your last slides you showed an improvement score, and you were 57% better than climatology 57% of the time, or something of that nature. Your 6 month forecast over your number of sites. But if I'm interpreting that correctly, that's if you had a purely random forecast, presumably you expect that to be better 50% of the time. So that's sort of a 7% improvement on a random forecast. And if that's 7% over a limited number of sites, what was the chance? Is there a reasonable chance that could have been derived by chance, simply because you've got a relatively small number of sites? It just seems strange that sometimes the predictor seems to drop off in month 5, then return in month 6. I think you have the same pattern on the seasonal forecast. It drop off for a period and then come back again later on. How far have you pushed the statistical significance testing of these numbers?
Okay, the improvement is because we sell this data, and we know that the climatology data is free for everybody to analyze. So at the end, we need to be better than climatology. If we are not better than climatology, we cannot do anything about this data. So that's the thing which is important for us. Then it is different if we use 1 month ahead or we use the 6 months ahead predictions or a skill. So at the end, we look for a general point of view in a global way to look if we are in a good way to predict wind speed anomalies or no or not. That's the reason. I have shown you a very good one with a very high metrics, but I also had show you the average for all the globe. In some places we have no skill. In some places we have a very good skill. But at the end, the average numbers are more or less the same. If you are using Vortex model, which is a choosing of between the models and a mixing between the models, you are going to have this improvement over using the historical data. At the end, this is the final result that we have found. It is not for one specific place and for one specific month. It is for a long-term period, and maybe not only for one point and for a region as well.
Okay, may I ask you, is the methodology published, or is that a sort of secret source of Vortex? It'd be really interesting to follow up, because if there is genuinely monthly predictability 6 months ahead, that would be quite a major. I mean, I don't know if others here would agree with this. That'd be quite a major breakthrough. I've never seen that before anywhere, I don't think. As a global-ish result, as in something that's generally replicable because of the reasons.
Okay, it is not published. We are still developing that tool. The main things I have told you, but we have machine learning experts working on that, and we are developing. So it's going to change in the following years. We are only in the first step, and we did go public last year, so we only have 1 year experience with customers, but we are still developing that. we are a private company, so we have not still published that. We are going to publish that, but I don't know the detail of the policy.
I look forward to reading it when it comes out. Thank you.
You're welcome. I think for you, sorry, if you want to analyze this tool, contact me and we can set up a place for you to test this information, and your feedback it will be very grateful for us.
Great. Maybe one more question. You're talking about customers a lot. What really are the problems that the customers are using this tool for? What are the value propositions in the customers, and how do they derive the value?
Okay, we have different kind of customers. We have from operational teams in the wind industry. We also, it's kind of our customers for all other Vortex products. So the operational department of wind industry, they want to know how performs the wind farm and how it's going to perform. So maybe they need to update some budgets, or maybe they need to do some maintenance for that. So some of our customers are operational departments from the wind industry. We have also reached to some energy traders, because at the end this tool is also very good for energy trading. So our customers are from energy traders till operational and maintenance. There are also other developers of wind farms that they want to know how it's going to perform in the following year while they are designing the wind farm. So we have this kind of different customers.
Okay, thanks. And with that, thank you again.
You're welcome. Thank you.
And we are getting to Enercast.
Now, can you see my screen? Hello?
Yes, now it works.
Yes. Great. Oh, yeah. Okay, so. Okay, sorry. So hi, everyone. So I'm very happy to be here today to present our work on statistical downscaling for seasonal wind power forecast, case study in India. So our company, Enercast, has been providing short-range and medium-range energy forecasts for wind assets and the solar assets to our customers for years. And recently, we received requests from different customers for seasonal energy production forecasts, which led us to initiate pilot projects. So today, I would like to share the results from one pilot project we conducted with an Indian customer with you. And these seasonal forecasts are crucial for our customers as they help in reliable budgeting, optimizing wind park operation, and mitigating financial risks. For example, we got feedback from one customer that they would consider really to shut down the wind park if the monthly energy production below certain values. And previously, our customer did their yearly financial planning based on historical data from the past few years. However, they found the actual situation often differed from previous years. That was, of course, not surprising for us. Therefore, accurate forecasts are necessary. But directly using seasonal forecasts from climate models is quite challenging for our customers due to the unavailability of required energy forecasts and missing wind speed data at turbine hub height. Additionally, the numerical model output has coarse spatial resolution, with the pack sizes typically being much smaller than the model resolution. Moreover, the seasonal forecasts often contain like systematic error across different time scales. To address these challenges, then we focused on converting wind speed forecasts into site-specific power output. So at the data level that we experimented with seasonal forecasts from different providers, such as forecasts from Japanese Meteorological Agency and the Environmental and Climate Change Canada, and of course the ECMWF. But eventually we settled on using ECMWF for this pilot project, as it offered the best estimation. We used the wind speed data from surface level and pressure level as input for our model. And to mitigate systematic errors, especially at the monthly scale, we employed monthly forecast anomalies instead of absolute values. In addition, that we made effort to collect turbine level meter data from our customers and implemented in-house data cleansing steps. And on the method level, we constructed a statistical model by selecting the best model with the minimum mean absolute error from a list of machine learning methods. And before we start the whole project, at the initial stage of the project, we focused on evaluating the forecast scales of ECMWF seasonal forecasts over the India region, especially for the summer monsoon systems. And below there is a paper, very important paper for us. And this paper evaluated the forecast scale of the Indian monsoon and its onset. And indeed, we see the forecast scale of the IFS system in predicting this dynamic system. So it's important to ensure the quality of the site data we used for model training for the project. And the pack level aggregated energy data provided by our customer was insufficient for accurate predictions. The upper figure showcases an example of the turbine data on the left and the right side of the ideal power curve, caused by the factors such as wind plant shutdowns, incorrect data logging, and grid issue and operational situations. So to address this, we collected turbine level meter data and implemented data processing techniques, including removing outliers, handling missing values, and applying statistic techniques to improve data quality and reliability. So we applied the data cleansing procedure to more than 800 turbines from our customers. And that brought really value in enhanced accuracy of our energy production predictions. So this slide simply illustrates our approach in this project. It involves establishing a predictive relationship between seasonal forecast variables and the wind side power generation. So we generated, as input data, we use the seasonal forecast from the climate models. In addition, we generated time-related features using error 5 as additional input, and utilized various machine learning techniques to build the statistical relationship. So our model were trained on historical data to establish the connection between factors from forecasts from the climate model, such as wind speed at different levels. And then the target is the power generation in the wind parks. So based on the build model, we downscale and convert the seasonal forecast to site-specific energy production forecasts. We have been delivering these forecasts to our customers since the beginning of 2022, so beginning of last year, and covering always the next, the upcoming 6 months with monthly updates. So on the map, you see our Indian customer operates 11 wind parks across the Indian subcontinent with a total capacity exceeding 1,000 megawatt. For evaluation purposes, we slightly scale down the original portfolio to 1,000 megawatt. To assess the performance of our forecasts, we compare them with actual observations. But the baseline for the comparison is the climatological energy production calculated by downscaled hourly resolution area 5 wind speed to the site level, and then we converted it to power generation. So in the bar plot presented here, we evaluate the forecast for total energy production for over a 6-month period at the country level. The blue bar represents the climatological error, which is the difference between the climatology and the actual energy production. The green bar indicates the error between the seasonal forecast and the actual energy production. So it is obvious that the climatology error is higher than the error in the seasonal forecasts, especially for the months between May and September, which corresponds to the summer monsoon season, also the high wind season. So we also have the evaluation results for the monthly energy forecast at different lead times. We evaluated the forecast for lead time ranging from 1 to 6 months, and the results looked similar. So here we present the figures only for the 1 month and 3 months lead time. So the gray bar represents the actual energy production, while the light green bar represents the climatology and the dark green bar represents the seasonal forecast. As you can see that the seasonal forecast accurately captured the trend direction for most months. But however, the relative error varies from 2% to more than 30%. Okay, nevertheless, the 7 out of 11, we calculated 7 out of 11 months, the error is below 15%. And for the 3 monthly time, the error is below 15% in 6 out of 9 months. So we can see that the seasonal forecast outperforms the climatology in most months, particularly during the monsoon season for both lead time cases. So finally, here's a brief summary and outlook for the future. So based on the evaluation results, it is evident that the seasonal energy forecasts outperform the climatology in most months, especially during the high wind season. And this holds true for lead times ranging from 1 to 6 months. The seasonal forecast offered significant improved estimates for 6 months energy production compared to the climatology. And so these estimates were useful for our customers do annual budgeting and financial planning. So in the next steps, we would like to evaluate the seasonal forecasts in extended horizons and initiate more pilot projects in other regions. And currently, we also just provide the best estimation for each month. But in the future, we also aim to offer a range of forecast uncertainties for on monthly basis. So that's it. Thanks.
Thanks a lot. Do we have questions from the room? Then let's start with one from the chat.
Yeah.
And the question is your historical site data proprietary, or is that provided by the customer? And if so, how do you do it if you get a new customer that doesn't have abundant historical data?
We got like 2-3 years historical data from our customers. It's like 15 minutes resoluted. And then we used, we built a model to connect the error 5 data, reanalyze data with the customer data, and downscale and convert, the error 5 wind speed information to the energy production information. Then we could build a historical energy production data set. So or else it's or else the customer's data would be too short. That's a problem. If the customer does not have data, then it's difficult to apply to use the same method.
Okay. As I don't see any more questions, then thank you again. And Alberto, please take it away. Alberto Troccolo is from WEMC, the World Energy Meteorology Council, and he's also having his little consultancy company, ICS, which you probably can better explain yourself.
Okay, thanks. Sorry, Gregor, it says that I cannot share what other participants have shared.
Juan, could you please? No, well, let me see that. Oh, that's better.
Okay, so thank you, Gregor and John, for the invitation. And I don't know how much time I have though, because I was supposed to start some time ago. I'm happy to be flexible. I can reduce it to 5 minutes. I was told at some point that it was going to be 20 and then 30, 35. So I'm not really sure. Can you give me an indication?
Oh, I think 20 should be fine.
All right. Okay. Yeah, I'll probably keep it shorter. I've got a lot of results here. It's not it's a mix of kind of research results, project results, and a bit of applications, and also blended with kind of co-production discussion. So like Gregor said, I represent the World Energy Meteorology Council, but also Inside Climate Service, which is a startup based in Italy, working on climate services, as the name implies. So energy and other components. I was going to show this, but yeah, you're probably all familiar with this, looking at the audience. So I'll skip a few and start with this one, which is basically going back to the Seclifern project. Some of you are already well familiar with this, but I'll say a few words. And so this project started with the idea of looking at the potential of seasonal forecast, and particularly the added value in terms of economic and other assessments. and we actually started from an industry demand because there's some big swings in gas price, as you can see in the middle panel here. I don't know if you see the pointer, but there is a big swing due to the heat wave in 2015, and obviously here we're not talking just about wind. That's the other thing. I wasn't sure whether this was just wind or not. I saw mixed things, so I mixed. I'm not focusing specifically on wind on the presentation. So let me know if I mean, I'm happy to cut it short if it's not relevant. So yeah, so this basically led to a discussion about what we can do. Can we predict this kind of heat wave and then gas prices, not just a heat wave, but also using that information into their the models, econometric models that energy companies use to see whether they can reflect the input from seasonal forecast into gas prices, but also renewable energy generation. And so we set up this projects with 9 case studies, most of them over Europe, and 1 or 2 over South America and Colombia. And there was a mix also of industries, some related to hydropower, some related to, like I said, the gas power and gas demand. And others also strong winds like here, or the effect of El Nino in South America. So I won't discuss the details of any of this, but I'll tell you where you can find more information later. And in terms of co-production, I guess, yeah, this is what a lot of the projects that are funded by the EU and similar are focusing on, is to basically spend quite a bit of time with users, potential users, stakeholders, and various people who are interested in this climate services, in this case seasonal forecast, and discuss what how they can be presented and so on. So this is an important part of the discussion, which of course happens on a one-to-one basis with private companies, as in with the examples we've seen in the previous talks. Here is more kind of group discussions, and then they're also one-to-one, but it's trying to understand also what is important and relevant, and then these lessons are useful also for the development of commercial products like those we've seen. So hopefully some of this also percolates into the activities of the commercial companies. So this again, that's just the standard process that is used in kind of research projects, where you follow certain steps in order to go from understanding on the user requirements and then creating a service at the end with various steps, iterations, and so on. So we looked also at, like I said, we wanted to assess the value of this of the seasonal forecast, so for the different case studies, and so we looked at different methodologies in terms of assessment from an economic point of view, and within that we looked at different models and methods to assess the value depending on the problem, because some have some of the case studies could share more data, and so it's easier to assess the value. In other cases, we had to kind of derive from the discussion what would be the value. So we weren't able to assess the value, economic value for all of them, but one of the important lessons that came out is that there is interest, a lot of interest, even if it's not quantifiable economically, there is interest to use seasonal forecast. And again, the examples we've seen in the previous talks is, I guess, testament of what is happening now, that more and more people are interested in these products. And so, just to also emphasize again, the role of this project is not, it's important to provide some numbers from an economic perspective, but it's also important to engage with the users and show what is possible, what are the limitations. That's also obviously something that we discussed a lot, what the limitations of the seasonal forecasts are. And in spite of that, there is interest, because there is some value we've seen also before. So here I just show some of the research questions that we addressed. Briefly, we looked at how we could estimate the independence of the seasonal forecast. So when we have multi-model combinations, we know that sometimes adding new models doesn't give you anything, and why is that? And so we looked at some of the reasons why this is not happening, and this was done with this new metric that is called Brass cube score covariance, and it basically measures how independent one model is from the other. And we looked at we took many models, more than 10 models here altogether, and looked at the many combinations over many variables and many regions. So this is something that is being still written up with a little delay, but it's coming out. I mean, there's going to be submitted very soon now, this paper with all this analysis, with all these models, where we looked at how this measure behaves around the world, and then we look at various regions. Like here, for example, this is a kind of summary. So what we've done is to compute the combinations, all the combinations of the models we've seen. And so if you look at the top graph, it's pretty busy, but it contains a lot of useful information. And on the y-axis, you have the number of models in the combination. So starting from 1, and you see what is the, if you were to take the one individual model, this you can choose which is the best. But then you go to 2, and it's not necessarily the top one individual model that gives you the best combination with another one, and so on. And in most cases, what we found is that there is a kind of saturation at around 3 or 4 models. But of course, the problem is that they're not always the same, and so it depends on the location variable and so on, all these things. But if you train your models and provided they are stable enough, so there are some models like we know they change year after year, similar to weather forecast. So it's a bit more difficult to keep track of the skill of the models that change all the time. But still, if you set up a system like this where you compute the skill, all the combinations, then you can find for the variables and locations you are interested in which models you should use for that particular location, and you can avoid a lot of computational costs, because you can imagine if you use 11 models compared to 3, it's a lot of savings. So and like you see in this case, it tails the error or the skill actually goes down quite considerably if you add models. So it doesn't really make sense to add. How you choose them, then you do this first step, and you look at what methods you have. But then you helped also by the matrix here at the bottom left, which is what I was discussing before about the independence matrix. And this tells you, again, all the combinations of models, and tells you how independent each model is from the other. Anyway, without going into the details, the long story short is that as we kind of expected, and there were already other papers, but this has been quantified now in a more rigorous way. It turns out that basically the models that are don't share components like atmospheric model and ocean models and so on, contribute more to the skill. So independence of models leads to higher skill when you combine them. And so this is the case, for example, CMCC, here you see a higher value with many models, European models as well, because it's different from other European models. And similarly, if you take combinations of North American models with European models, normally you get better results than just taking, let's say, 3 European models with or 3 North American models. When you mix them, you get so like in the example here, for example, the best combination here at the top you see is 3 models. I mean, this is just one example. There are many more, but you can see you got 2 European with CMCC, which is kind of mixed, and 1 North American. So that's not always the case, but it's a good summary of the results we found. Okay, so then yeah, there are other similar tests. Another thing that we've done and now continuing to do is to actually combine observations with numerical models. So we like dynamical models, the numerical models, but we also we're also aware of the limitations. So what we do is that we take their output and combine them with observations within machine learning models, and they could be gradient boosting models or random forest or similar. And it turns out that we get better results in the end. In this case, we did the test to see how often or in which locations the dynamical models were performing better than observations. And there are many areas where they are, but again, if we combine dynamical models with statistical models, you get in general better results with observations. I mean, obviously you don't have observations in the future, but it's there is normally some lag in the information they provide, at least for the first few months into the forecast. So yeah, so this some of the results were then applied to this case study one, which I mentioned at the beginning, and it was tested for the summer 2015 with the different lead times, and this was a kind of extreme case of the heat wave, so just one case, but at least they showed that the forecast was going in the right direction, and it was providing more value than just using climatology, which is what at that stage this company was doing. And so it was beneficial for them to go towards this. Like I said, here you've got all the case study flyers and descriptions to some extent of this, of what was involved in each of the case studies. Then we also looked at the delivery of this services, and there were different types. On the left, you see some kind of innovations in terms of presentation of the skill, looking at how this changes over time. We've seen similar examples also before. So yeah, we got, without going into the details, it's just different ways to represent the results to make it more immediate interpretation for users. And on the right, then we also developed a visualization tool, a web visualization tool called Teal, which contains different modules. There is a public component which provides historical data as well as projections at some level, and then there is a seasonal forecast module that is being developed, which is more on the commercial side. And this is just to give you a snippet of how it looks, and basically you choose the dates and so on, the regions, and you get a simple prediction of the distribution, in this case of 2 systems, and on the top with reference from the past, and then the climatology, the anomaly at the bottom. And so this one was one of the main output from Cyclifirm, which is now continuing into other applications, similar applications. So we've done similar. We don't have seasonal forecast for this one in particular. We have at the moment historical and projections, but we developed this application for wind power and solar power for West and Central Africa. So this is available at the link provided, which I forgot to put, but I can give it to you. And then also other developments here under the Focus Africa project, which is looking at applications in Southern Africa, and in our case, particularly Tanzania, Malawi, and partly Mozambique. And we're developing this application currently mainly for related to precipitation, but it's going to be used also for hydropower generation and eventually also wind and solar. Mainly for, actually not at the beginning seasonal, but still. Anyway, so this is a different type of applications. This is for seasonal forecast, similar to what we've seen before. And you can have more information here. So the free version here, and you can play around. And just wanted to add also some of the work we're doing in the context of C3S, because yeah, this is a big development that we are undertaking, and there is two types of projects. Basically, the top row, which is looking at multivariable, multi-scale view of climate and energy systems, and this includes seasonal forecast, and it's actually going to go from the current European system to the global scale, with the first products coming out towards the end of this year, and it's going to run for other 2 years after that. So ending towards the end of 2025. And just for completeness, we are doing also another project related to this, but this is only for Europe, and it doesn't have a seasonal forecast, but it's relevant in the context of network operations and planning particularly. And so this is for the adequacy assessment, particularly with ENSTOI. Yeah, this is some of you know this, and this is the most important slide with announcement of the 7th International Energy and Meteorology Conference, which is happening in less than a month in Italy. There's still time to register. So I think I'll stop there. Thank you for your attention.
Thank you, Alberto. Do we have some questions here?
I have a question.
Yeah.
Thanks for the nice talk. That was interesting. I was interested in this independence metric for the seasonal forecasts. Can you say a bit more about how you implement that Breyer skill score covariance that once you calculate it, how do you use that to weight the different models within the ensemble?
Yeah, I mean, I should say I'm not the expert on this, but basically, we found ways to speed up the calculation. That's why we were able to do this computations of over many areas and many models and so on. And so I guess yeah, the methodology itself is pretty straightforward, and in terms of you know, the relationship that we apply, so that's basically like a Breyer score, so that's easy. But then it's how you classify, I guess, and all the model combinations, and it's a kind of mix in the end. You know, you do this exercise to understand roughly what are the main models and so on. Once you do this for a while, then you get the hang of it, and you probably then just do an educated guess about the models you want to use when you go to a new area and so on, and because if you don't have resources to run all the combinations. But I'm actually not sure I'm answering your question, and please let me know whether there was something more specific you wanted to know.
Yeah, I guess it's just because I mean it's an interesting idea. It's been used in future climate projections where you see that there's a real dependence between different models that have got common ancestors. But it occurred to me that on the slides you showed, the numbers were pretty small, so they look, you know, to be provocative, they looked quite independent, all of the different models. So I wondered if you could actually get anything from weighting them, but it doesn't sound like you actually do weight them in these combinations.
Well, no, yeah, no, actually we do. Yeah, no, we do. Yeah, sorry, yeah. So I didn't comment, but yeah, indeed, the values are, like you said, they don't look far apart from one another, but it turns out that small differences matter, and so it's down to how you basically weight them, because obviously, you know, you can rescale the values, and because we've seen that actually the small values, like I said, in the case of North American models, European, the metric itself doesn't discriminate that well in terms of actual values. But like I said, if you rescale them like we've done, then you can apply that in an automated way, which is what we've done also in the paper that is coming out. So I don't know all the details, but I can refer you to the first author is Andrea Alessandri from CNR in Italy, and he'd be happy to tell you more. But we are also doing one of my colleagues at WEMC has done a lot of calculations on that.
Thanks.
Okay. Just wanted to pick up on David's comment. I suspect when you pick a different set of the analysis observations and another representation of the real world.
Sorry, Anca, I cannot hear you well.
Sorry, Alberto. I was directing my comment to David, but particularly because I don't think you will have the answer. If you were to use a different truth for your evaluation, a different reanalysis, a different set of observations, presumably the weights will be somewhat different. So I just wondered, before you reject the hypothesis that the equal weights is a satisfactory, within error bars, satisfactory combination, if you've tested the sensitivity to the choice of data set of observations, very few people, I would say virtually none, build those into their evaluation, into the scores of the metrics. So I just, but you wouldn't know if you say that Andreas done the work. Maybe we need to ask him. But I thought it's a point worth raising here.
Yeah, well, I don't think we've done that, but I also don't know. I can see that some models may be, you know, have an advantage, particularly if you use ERA 5 and seasonal system 5 or whatever. But I don't see overall how that would change the big picture.
I think it's worth testing. That's what I was saying.
You must be lowering the skill scores though, because you're smoothing signal. If you use multiple reanalyses to create a single source,
well, not necessarily, just assess it against each of them and then see the range of conclusions you reach about your weights.
Yeah.
If the weights go up and down, then is it worth waiting? That's the point. I think we should start from the null hypothesis, given how little how small the sample of data we have, that equal weights would be good. And you need to reject that at some level of significance by testing it against all the uncertainties you can think of. Thank you.
Good. Then there are no questions. No, that's one. Alberto, in the chat, there's a question. Could you please provide some details about your project for future wind production? How much would you trust the prediction given known issues like GCM's biases and low resolution?
Well, I mean, is this, yeah, wind projection. So this wind, I guess wind speed or wind power, whatever, yes. Well, like in all projections, yeah, we can assess them, but we spent quite a bit of time on the bias adjustment and trying to ensure that they, you know, at least aligned during the historical period, and then we can look at whether there are some, you know, some funny behaviors when they go into the future. For wind in particular, there's not they're not huge variations like for in general as with temperature. So I mean, there's no, I guess, indication that we shouldn't trust them. They don't have any kind of strange behavior. But again, you know, this is the best we can do. Everybody can do. I mean, it's not. Just have to trust them.
Good. Then thanks, Alberto.
Thank you, Gregor. Thank you, everybody.
And this is the end of this session, but there's one more activity between you and lunch, and that's taking a group picture, which always is nice to get from these workshops. I don't know how we should do that. Is there any special place outside that we should go, or should we just be here and maybe have the?
I've no idea.
Okay, hello. My name is Lenaghan. I'm from National Grid. I work at the control centre, which is actually not too far from this spot, about 10 minutes down the road. I think many of you are coming to visit us tomorrow, hopefully, fingers crossed. So my talk is really going to be about some of our challenges rather than outlining any research. We're looking to yourselves to give us some more ideas on ways we can tackle some of the things I'm going to mention. So the first thing to say on right at the beginning for this slide is that the more renewable generation that we have connected to our national grid, the more sensitive it will be to the weather. I'm sure that's fairly self-explanatory to all of you. But interestingly, therefore, you can say it's going to be more sensitive to weather forecasts. And therefore, by extrapolation, more sensitive to weather forecast error. So have those three levels in your mind. We go through this because what I'm going to talk about now is a situation that occurred towards the end of last year on New Year's Eve, in fact, where we had some very interesting weather, and it wouldn't be regarded as extreme by anyone really, but it was extreme in our case, and you'll see why as I go through. So I'm not sure, do I just press a button to move to the next slide? No, you have control.
I have control. I'm just about to give you the control.
Oh, wow. Thank you. All right, well, let me, do I have a pointer as well? Does that work? Oh, yes, right, okay. Let me explain. This is the wind power forecast that is available on our website on New Year's Eve, a day where I happen to be doing the forecasting. And this comes from our BM Reports website. So if you wanted to see this chart equivalent for today, and you have internet access, you can always type into Google bmreports.com. And there should be a wind power forecast on available. But that's for later. For now, let's look at this point down here. This red line that you can see is the metered wind output. So for the majority of wind farms, we receive live metering, and we add that all together, and that appears as red line for the previous half hour of each day. So it's near to real time. The bars that you see, the blue bars are the wind power forecast that's produced at 48 hours ahead of time. And the yellow bars are nearer to real-time forecasts, maybe about 4 to 6 hours ahead. So the yellow line is the one to look at. And you can see this difference of about 3 gigawatts between our forecast and the output at that point. So it was about then when my colleagues in the control room phoned me up and say, what's going wrong with the wind power forecasts? Maybe they didn't quite say it like that, but they basically wanted to know what was going on. So I must confess, at that moment, I didn't know why this was occurring. So I decided, well, better find out. So I went to my favorite weather website, windy.com. Hopefully I can press the magic button. Oh, maybe press it again. Might need your help, Gregor, with this.
It only works on the certain circumstances.
Yeah, maybe it's fingerprint recognition. It's right. Okay, windy.com. Really fantastic website. I don't own shares in windy.com, but I'm happy to say they're good because I use them quite frequently in my work. And this white dot, if I just highlight the dot, that's approximately where the largest offshore wind farm is called Hornsey. And there's over a gigawatt worth of installed wind capacity right there at that spot. And the forecast that we're looking at, the wind power forecast, you can see, so it's just the wind forecast, shows windy areas in red and moderate in green, and no wind, almost blue. And it's a similar idea with these small indicators where that's measured wind for where there's a weather station in the airport. And you can see these are indicating measured on there. So we've got the forecast and actuals for wind speed all in one chart. Pretty good. You can see this one here says 1 meter per second, and the dot next to it has 0, which means that this particular weather model indicates there's 0 wind speed at that wind farm. So perhaps no surprise that there's no power coming from that wind farm. But let's move on to a different weather model, which I've got on the next slide. Let's try again. Brilliant. Okay, notice that 0 again, and notice the forecast wind area that has moderate wind in it is further north. And where it says measured wind speed is 0, actual wind speed is 7 or so meters per second. So with a wind farm that's bigger than a gigawatt, even with a mere breeze of 7 meters per second, you'd still expect quite a lot of power from it. So, and also I'd like to highlight this interesting line of where there's low wind above it and a fair bit of wind below. So I've spent far too many hours looking at weather forecasts, and I can't recall seeing before or since a time when there's this kind of wind barrier of some description happening before. I thought that was really strange. But it did explain nicely what was occurring, that the forecasts we'd received 4 hours ahead or even the day before, indicated Hornsey would have a moderate amount of wind. And then reality came along and said no wind. And that's why we got next to no megawatts in that wind. And that basically gave us a massive hole, not just for Hornsey, but for other wind farms in that area, where obviously the energy had to be found from somewhere else. And my colleagues in the control room were committing their reserves to fill in that big gap that we saw in the first slide. So, yeah, this was shall we say it was an interesting day. So I went to have a look a bit further. One thing I was explaining to colleagues just over lunch is that 95% of the energy that passes across National Grid is not bought or sold by National Grid. And that might be a surprise for you to hear that. This 95% of energy is bought and sold by market participants, either generators or suppliers, buying and selling from each other, trying to balance out their position. It's only the 5% that the control room get involved in to try and bring the market into balance if it's out of balance, or make adjustments to the grid for the smooth running of the grid. So with that, realizing that, I thought, well, I wonder what the market is reacting to this wind error. What is the reaction? And this does show some part of that picture, because they're also available on the BM Reports website I mentioned earlier. If you want to look at today's one, you can see them there. But these are the ones from New Year's Eve, and I wanted to highlight this that one. Oops. Oh, back. Thanks. That peak there, right? So I should explain. When the market, the generators and suppliers are out of balance, then it's the job of the control room to bring it back in balance. We have terminology for this. If the market has more energy than it needs, then we call that the wrong market, and it's the control room's job to buy that back so that it's balanced. And the reverse situation, we call it a short market. And that's what this chart indicates. Short is positive direction, which means the market doesn't have enough energy and the control room had to add extra energy to make it work. And long is bottom direction. So this is basically a short market that's gone, and I don't know if you can see the number, 1,800 is the top of the chart there. It didn't quite go that long, but it didn't quite go that short, but that's about as short as I've ever seen the market go. So what that tells me is this weather forecast error, the slight change of the position of where it was supposed to be windy and where it wasn't windy, has caught the market by a little bit by surprise, but not completely, because remember this number is say 1,700 megawatts, and the change, the difference between forecast and an actual for wind power was in the region of 3 gigawatts. So the market has half been wise to it and half been caught out by it. I thought that was very interesting. But that has another effect, which is worth looking at here. These are the system prices in a short-term balancing market. So broadly speaking, it's not precise science, but broadly speaking, the more actions my control room colleagues have to take to intervene in the position of things, the higher this price goes. And this price is set by the most expensive action that they have to instruct. So the peak of the chart on the right coincides with the peak of the chart on the left, as you might expect. Short market means controlling appetite for action and prices go up. So this is one of these rare cases where you can actually trace through the consequences of a inaccurate forecast for wind speed, turns into an inaccurate forecast for wind power, turns into a error in the market, which needs to be corrected by control room colleagues, that indicates the market is out of balance and thus pushes prices up and makes it more expensive. So it's quite rare that actually the chain of consequence is as clear as this. Most of the time, really difficult to work out what caused what. But that's why I thought I'd show you this example of these things, how they influence each other. So, oops, press the right button. Let's see. Now, this is the demand forecast. Another interesting aspect. Let me draw your attention to the black dot. Right, the black dot is what we call a cardinal point. So just to fill you in the world of demand forecasting, we don't explicitly forecast every single point in the future. We forecast cardinal points. We call them cardinal points. They are the turning points in the demand curve, peaks and troughs, with a few exceptions, which are fixed points. And this is the morning point, coincides with about 10 in the morning. And this red line is the measured demand up to that point. So I was looking back, reviewing where it all went wrong in the morning, and this is the time when that wind power forecast was there. So interestingly, the market did respond to the situation, not only in terms of generation, but since we have lots of an increasing amount of storage installed on our distribution network, I think that is actually the end of the chain where electricity prices went up. Storage responded by saying, this would be a good time for my full battery to start pushing energy into the grid. And that's why I got my forecast wrong at this particular point, because it would normally have followed one of these historical curves, and that's what the coloured lines are, the New Year's Eve days of previous years. Why did the reality of New Year's Eve last year follow this different path? And I think it was the market of energy storage responding to it. And because all of the storage, all the lithium-ion batteries and other storage technologies are connected to our distribution network, when they start pushing energy into the grid, it doesn't appear on our national grid meters, it just appears as a reduction in demand. And that's what's happening here. So another interesting thing to add to the end of this chain of consequence and influence that New Year's Eve has revealed. So, yeah, I keep pressing the wrong button. So again, this is another system we use internally for forecasting, and yeah, and that also illustrates a little bit of what's occurring. Yes, so I won't go into too much detail there because it detracts from the meteorology. Right, let's go back to the BM Reports website. There's some other interesting charts worth looking at there, which we can look at in real time if you like. But this is, again, these are charts for New Year's Eve, and this is our plant mix. So it's worth remembering that really there's two curves at work all the time. There's the demand curve, and then there's a generation curve. And my colleagues in the control room work very hard to keep them matched all the time. But this chart focuses on the generation phase, and it really shows what kind of mixture it is. So you can see on New Year's Eve that one thing that did reduce quite a bit was that blue. You can see compared to the day before, the 30th of December and New Year's Eve, halfway through, wind reduced in the middle of that. And that kind of matches up with what we've seen in previous charts. Where that's really interesting is when I adjust this chart, Statistical on the website, allowing me to untick a lot of these boxes. I can just look at the short-term generation. So I've got 4 boxes here: pump storage, so fast-acting hydroelectric power stations, OCGT, which stands for open cycle gas turbine. So again, they're very fast-acting, a bit polluting and a bit expensive, but still, if you're in the control room, they're one of the go-to tools they use to push energy into the grid. And there's also hydro non-pump storage. So we have run-of-river generators in Scotland, standard hydro, really. And then there's other, don't ask me what other things for. But it does tell the same picture, that as the market went short, as the wind error got large, my colleagues in the control room had to instruct plants and instruct expensive and polluting plants. So I suppose that's the end of the chain of this whole story. That's an error in the wind speed forecast rippled all the way down the chain and had an environmental impact and caused an increased amount of pollution to occur. So it's all now a big cycle. And this is the only time where I've seen this whole thing connect up, just like that. So, really, that brings me to the point for any questions.
Thanks for a very nice story presentation. But I'm frustrated because you keep saying the weather forecast is wrong, and I haven't seen it. What I've seen is a forecast. There would be an ensemble, and there should be a weather forecast as well, interpreting the synoptic chart and seeing where the front is and all the risk. So I don't think without seeing that the weather forecast was wrong, but they used the wrong information.
I think that's a fair point, and I've been slightly disingenuous in saying that things are black and white, right or wrong. I know from listening to all of you today that the weather forecast is much more nuanced than that. One of the things I haven't explained is that many of our systems in the control room are built in a time when we didn't have ensemble forecasts. We worked with deterministic forecasts. We draw a single line into the future and say that's what's going to happen, and also hold reserves around that to cover every other circumstance. And I don't know if any of you have ever been involved in updating IT systems in large organisations like National Grid, but it's very expensive and time-consuming and has a lot of challenges. So where we are today is to try and feed in the best information we can get, and I appreciate there's more to weather forecasting than I'm showing here today. But we have to filter that down into a very small funnel, which is basically still operating in a deterministic way. So I suppose that's the bad news I have to deliver to you. That for quite some years, I think into the future, our current systems will be very deterministic. even though there are ensemble members, a huge amount of great information that we could draw upon, we perhaps need to be not only clever at rebuilding our systems anew to take full advantage of that, but also before we get to that point, we need to be good at making the ensemble members fit into the systems we currently have. That's our challenge. It's very quick. I'm sorry if I hate to upset any meteorologists by saying the weather forecast is wrong. Another question.
I'm very angry, honestly. Two questions. Can you describe a little bit more about the process you're actually using to forecast wind power and so on? Is the first question. And then the second question is, at what point does the cost of misinformation become more expensive than the cost of not fixing the internal system?
An easy question and an impossible question. So, right, okay, I'll answer the easy question first. So for our systems that we have for forecasting wind power, they were designed in the year 2010 and 2011 with the technology we get hold of at that time. So it's an Oracle database with a web-based front end, and we had to make some very difficult design choices at that time. The weather companies we approached were willing to offer us ensemble forecasts, and every single ensemble member in a massive file for every grid point that we wanted. I was involved at that time trying to scratch my head and think, well, that's great, but these servers won't cope with that for more than a week, and then they'll just be full, or even worse, they will take so long to convert a wind speed forecast into a wind power forecast that the wind power forecast won't be ready when the next wind speed forecast comes in, and then the system will just get stuck. So we needed to be practical. We needed a system that would deliver the forecasts to our control colleagues. So we took a difficult design choice. We asked the weather companies to, instead of providing us with individual ensemble members, we said, can you convert that into what we call deciles? So percentiles from 0 to 100% at 10% intervals. Give us 11 lines plus the mean forecasts, and we'll feed that through our systems and turn that into percentiles for wind power. And we'll do that for every large wind farm that we forecast. And essentially, that's what we do still to this day. And we are now getting to the time where we think, well, maybe that decision wasn't so great after all. We need to go back to the ensemble members and get more information through. Where we think we'll get an advantage in revisiting that is when there's ramping effects. So we have our largest forecast errors on those days when it goes from low wind to high across the whole of Great Britain. And the timing of the ramp is out by a couple of hours, and then we obviously apply our root mean squared error, and we get like a massive spike of error, and everyone asks, what did you get it wrong? Oh, sorry, I use that word again. With the possibility of individual ensemble members, we could get an idea of the variability in timing of that ramp. And we're just on that journey now to see how far we've gone. Right. Going back to the impossible question. Yes, it's been a bit of a mission over many years of mine to try and figure out a clear relationship between forecast error and cost. And I'm sorry to say, I've come to the conclusion that with the exception of a couple of rare circumstances, it's very difficult to draw a direct connection between the two. Because really what would be fantastic is that if I could say I could reduce the error by half, therefore I could save this many millions of pounds. The problem is, it's not as simple as that. What I found is that on many days, reducing the error does improve things, but something else is going on the grid, which costs costs a lot of money for a different reason, and then it becomes quite hard in the mix to decouple what saved money and what would save in different circumstances. Every day is different, so it's very hard to say one action will have guaranteed one result, and this is another challenge of mine. But at the same time, we're still committed to try and improve things. Of course, so I'm really open to any further suggestions of what can be done best, and most importantly, what can be done better for a modest amount of effort for us. So I think the gold-plated service, we just can't afford that. Sorry, yes.
I have a question. These are if the forecasts are bad, for whatever reason, or off, National Grid then has to take all of these balancing actions or call on CCTV for overall. Are there any financial implications for National Grid at that point? Because for a commercial, an energy trader, they have to buy back or sell power at a high price, make a loss. That obviously feeds back into us. That then is the driver for, it might not be the energy traders' fault, they will feed back to business, say that we need better weather forecasts, or we need probabilistic forecasts. To do that, we need better servers, more money, more investment.
Yeah.
Is there a feedback loop like that for National Grid? Are there any, I guess, penalties or financial implications from not taking that action?
Yes, there's what we call an incentive scheme set up by our regulator. We're incentivized to, broadly speaking, run the National Grid at the lowest reasonable cost, and avoid unnecessary expense. There are some days which, that was one of them, but there's some days where it's just going to be difficult. And when faced with a difficult choice of keeping the lights on or blacking out the country but saving £100 million, then it's going to be difficult. Thankfully, it hasn't quite got to £100 million today, but there are days where you'll be able to see from our publications on our website that it's been 20 million one day. Those are the kind of costs that we're talking about when the day is tough. But largely we can run it more cheaply than that if things are running smoothly, armed with a nice forecast, and if things go to plan, and everything works as we would hope, then costs will be lower.
But 20 million is covered by the market, the end consumer, right?
Well, broadly speaking, the money that we spend running the system comes from a slice that everyone's interested in.
Yeah. So is there what's the financial or the implication if it went to 20 million, so kind of unnecessarily? What's the feedback you then to get National Grid to make changes?
Well, we always have internal reviews to make sure that unnecessary spend is learned from and not repeated. And sometimes, with the benefit of hindsight, you can see that the grid could be run in a more efficient way. Hindsight is that wonderful thing that things look easier in hindsight than do when you're in the moment trying to figure out what's next. Yeah, there's internal reviews, but there's also our incentive scheme, which means that if we're successful at running the grid more cheaply than our target, we have an an annual expenditure targets that's negotiated. If we could save money and come in cheaper, then we can keep a percentage of the same. And that's kind of a, it's not as tight a feedback loop as for a trader who sees each trade, whether it's good or bad. It's more longer term. So yeah, we tend not to have the tight feedback loops for that sort of thing. Although at the same time, control engineer is sat there sending instructions to individual generators all the time. And if a bad one is sent, then they do very quickly know about it. There's a kind of mercifully rare situation called we call it a manifest error. Basically, that's a situation where the control engineer instructed the generator up or down by mistake. And thankfully, this is the kind of thing that happens maybe once every 2 years. And they're sending thousands of instructions each day. So it is a testament how good they are at their job to achieve like 99%, or 99.999% accuracy. But we have a process for dealing with that and unwinding those mistakes. Thankfully, they're pretty good. Does that answer your question?
Yeah, thanks. That's very good.
Yes. For order of magnitude comparison, 2 years ago, when it first got the Texas electricity bill, there was a deep freeze that drove up demand. Well, it drove up demand, it froze natural gas supplies, and frozen precipitation locked up the wind farms. The estimated cost of the outage that occurred is $1.25 billion.
Yeah.
So it's like that's the scale of what can happen. Caused by weather.
Yeah, completely. It's very difficult to estimate what the power, what the expense of a Great Britain blackout would be. Thankfully, never happened.
It would probably force change though.
Yes, or would it force good change or bad change? So I use that word.
Yeah.
So yeah, it's very difficult to answer some of those questions unless you've got a complete replica of the national grid and you explore the disaster scenario to its fullest. Otherwise, we're just guessing. But sometimes guessing is all we have.
Okay. Yes. Yeah. So you showed that basically the poor error at Hornsey was the problem there, and that actually the other sources like pumped hydropower filled in. I thought kind of the hypothetical situation, if you like, we're obviously trying to build more wind farms all the time. If the Hornsey, in this example, if Hornsey was say 4 times the size, is there enough alternative sources to kind of come on board quickly? Like
that's a very good question. Yeah, there's another conversation I had over lunch was one of the things my colleagues do in the control room is to look at the largest loss. What is the largest generator pushing in the largest amount to the grid at any particular moment that could possibly be disconnected at short notice, maybe because of a lightning strike or plant failure or some other problem. And they hold reserve for exactly that. So on certain days, the largest loss might be like a nuclear power station. And on other days, it might be Hornsey wind farm. And my colleagues have to make this judgment. Whatever the largest loss is, needs a certain amount of reserve to cover it, which disappear. So you can try to minimize your reserves, but you might also save money by preemptively shutting down the largest loss. So the next largest thing is the thing you have to cover, and therefore you save the amount of reserves you cover. But then you have to pay an extra cost at starting something else up to cover what you've just shut down. So it's kind of a complicated game of kind of sliding block puzzle style operation to try and minimize the cost of holding reserve that you need and making sure it doesn't, making sure you're not caught out.
Two things. One is a question here from the online audience. Given your tech constraints, would it be possible to substitute the best forecast with a low probability but high impact extreme ensemble member? That would still be only one curve or one probabilistic curve, but could that gauge the critical risk better?
Yes. Yeah. There's something I haven't told you. Well, it's so difficult to explain everything that goes on the grid in half an hour. But as I said to you earlier, that many of our systems that have are deterministic wasn't quite true. Many of our systems have possibility for receiving three curves, an expected level, and a maximum and a minimum. So we do have some essence of probability that you can feed in the system for decision making. At the moment, the wind power, the maximum level is set to the 70th percentile, and the minimum level is set to the 30th percentile, with the expected level being the mean forecast. We decided on those through just a period of review. It was 80-20. Controller wanted a little bit more fidelity, but there's nothing stopping us reviewing that again and deciding if an extreme situation was apparent in the weather forecast coming through the day ahead, we could revise those percentiles accordingly and represent the greater uncertainty that might be coming our way. But still, it's not science. It's a bit of engineering. It's a bit unscientific. But it's what we have at the moment. We could do this.
Okay, and the other question is, are you actually using any seasonal or sub-seasonal forecasts, so longer term than just day ahead, what you just showed?
Okay, that's a good question. My colleagues in another team, the National Grid, their team is called the Future Energy Scenarios team, and they look much further into the future, look at energy trends over 10 years. They're the team that are really interested in seasonal forecasts and what you've been saying about decadal forecasts too. Yes, I'll have to defer to their greater knowledge, but if you do want to read their publications, they're available on the National Grid ESO website. Just search for Future Energy Scenarios, and we'll see what they do. They do marvelous work in that area. Okay. Okay. Yes.
So I wonder, how does the National Grid plan for their operational reserves? And for example, do they incorporate uncertainty and forecasts into planning for operational reserves, or as was done in the United States, is it percentage adder and often static for the period of time?
Yes, good question. How it used to be done, I think probably a good place to start. For electricity demand forecast, it was a simple matter of looking at past performance and looking at past errors in our own forecasts, and then holding reserve. And we had a standard 1 in 365 list of the plan to, and that just they gave us very simple bands around the forecasts as to where reserve, how much reserve that we have. And there was some taking account of run rates in the morning, a bit more reserve was we would hold there because starting the power stations sometimes they would be able to start and glass, so needing more to fill in the gaps. So, and that's probably how it was done for many years. When wind power came along and started to think, well, do we need extra reserve for wind power and wind power in short floor? And we started by
was saying, well, 30% of whatever we're forecasting, we hold that much reserve. And that's what we were doing back in 2011 when we just started. And we started to realise that we were getting reasonable at forecasting and power. So we'll trim that back to about 10. With a dead band of problem, basically the wind power output was less than 500 megawatts. We would say don't bother holding any reserve on it because we're already holding reserve for the other reasons. And that could easily be used to cover any loss. And when the wind is low, much more likely to increase. So it's developed even more expansion. So that's kind of where we were in about 2014, 2015. And then we thought, well, we started getting into this probability with the idea of these percentiles. Some days they'll be on lines, the days that we try that. We started to learn that some weather, some types of weather was very predictable. A big blocking high pressure system was sitting over the UK. The wind would be quite low, but it would be really predictable for a long period of time. And we could trim back the reserves even more than the 10% we have a policy of holding. Because it's going to be really reliable megawatts of wind for that time. So over the years, as we've learned, we've trimmed back the reserves. And I think there's still a long journey to go to try and know when to hold even less reserve and save money in doing that. And for when something unexpected and extreme is going to appear, where we really should be holding a lot more deliberately. I think there's more work to do. Okay. Maybe I could take future questions.
Yeah.
Yes. In my class.
Thank you.
Is this slide show as you? Just a second. Okay. Well, I can start by kind of explaining a little bit about my story. I think the story time has done a lot because it's a story as well. But I should start by saying something completely different, because what I would like to talk about is the other end of the line. We heard about right now the balance market, which is after the price has been set the day before. I talked to some of you yesterday, and how to price be set on energy. It's a long story, but a very short way is to say that it is when supply meets demand, they meet at a certain price, and everybody's happy, and that's the price for that certain hour. And that's kind of how it works in every country in the world. There might be exceptions, but in general. The balancing market is after that has been happened. Beforehand, that's where we are in the language I speak with my colleagues in the forward market, which means what is going on many weeks or even months ahead. And looking at the price mechanism is kind of the same. You look at what is the supply, what is the demand, and then it fixes that. But that's not the whole truth, because there is what my trader colleagues would call the risk premium. And I think that's relevant to mention, because I heard a lot about the extreme cases and what are the extreme cases. In the trading and in the price settlement, when we are out on the price market looking months ahead, is whatever would drive some huge price differences. It could be a heat wave, could be a cold spell. That would be the two typical major drivers of some long-term trends that would drive up prices. Could actually also be something like that we have, let's say, take a holiday period, and that holiday period would have a lot of wind.
A lot of winds would mean that prices would actually go to zero, depending on which country in Europe, it would go negative, which means that you would have, let's say, Christmas. If you have 10 hours with negative prices, I mean, if you could imagine that we have a price in, let's say, Germany around Christmas, let's say it's 100 euro per hour per megawatt. If you suddenly have some hours that go to zero or go to minus 200, I mean, that's a huge change on the average pricing of the whole Christmas period. So the extremes are very important when we talk about long-term. So that's why I have a small story here, and then I have over 2 slides with my kind of wish list. So let's take that afterwards. But if we take the next slide, do I have? I have the touch as well. Yeah. Just to put some context into this, because I thought, okay, what would I talk about today? And then I looked at my screen, and right now, what I've been doing since start of April is actually to look at the hydrological situation in the Alps. Now, I know that for many of you are more interested in wind than hydro, but it could be kind of the same. But right now, this is the best case I have right now. So let's start with that. To put it into context, the hydrological situation this year depends very much on what happened last year. Because last year we had, well, let's start with this one. This small graph shows the River Rhine in Germany. How much water is there? And the typical level, well, I can tell you right now, it's somewhere around 2.5 meters, which means that the River Rhine is used to a lot of stuff, but they have large barges of coal to be transported into the coal power plants in Germany. That's kind of the main way of transporting the coal around in Germany. So you need some water in these rivers for that to be possible. And usually that is possible. As mentioned right now, 2.5 meters, that's plenty. They have 2 levels where it's getting critical. The one is 1.20 meters in this region. It's a specific point called Huan. But let's just say 120 centimeters, that's when it becomes critical. And below 80 centimeters, they cannot transport any coal anymore to the coal-powered power plants in Germany. So what I can show you is that last year during summer in July, we came below 120. Actually, we reached 75 centimeters. There was no more transport in half of the Rhine for several months. That meant in itself that coal-powered plants had a problem getting enough. Then something else happened, and it all, of course, relates to this drought that was happening in all of Southern Europe. And that was that since there was very little water in the rivers, there was also small amounts of water heat up easier than large amounts of water, of course. So that meant that since it was very hot, the river temperatures rose. And a place where it's very significant, well, the Rhine is one, but the Huan River, they had its problems as well. And this is from, I guess it's August, yes, in the beginning of August. I just took this from the messages side of EDF, the French TSO, and they published that some of their nuclear power plants were to be reduced in the power output because they could not use the rivers for cooling anymore. There are 3, I think, power plants, nuclear power plants alone on the Rhone River, and they all use river water as cooling. And if they use river water and it's already 28 degrees, you will see fish boil after the power plant, after they just put some of the cooling water out. So they're not allowed to do that. So for environmental reasons, they put out this message. And just to put it into context, what actually happened is that power prices went so high that there was a new message afterwards, after a week or so, where they said, well, maybe a pity for the fish, but we rise the temperature limit so that you can actually produce anything. But this story, that's why I'm showing you this slide. The story was that there was actually a huge let's call it power crisis due to drought in Europe, both in Germany, also in France, many places, also Italy, due to the drought last year. So that was the context of how we looked at summer 2023. So if you take the next slide. This was what I was looking at. Not all of it, but still. If we look at the, this is all copied in. This one is copied in from one of our providers from the private company. And these are the ones perhaps taken from the ECMWF page. Just to show you where we were, this was the 1st of April forecast for April, well, for summer of 2022. And you can see that there was no doubt in the forecast of that we would have, especially in the beginning of the summer, a very dry summer. That turned out correct. So it is not a wrong forecast or anything. It's actually a pretty okay forecast. It is correct. Just to put that a bit here as context, well, the current forecast looks like that. It was again from the 1st of April. You can see it is drier than normal, but it's not much drier than normal. However, 1st of April, the amount of snow in the Alps was almost zero. Not completely zero, but there was a huge lack of snow in the Alps. So even a normal amount of precipitation, or at least not something that would go above normal, would mean that the Alps would still have a hydro problem this summer. And there were, I didn't include some temperature as well, but you may have seen that the ECMWF and other seasonal forecasts, they also expect a warm summer this summer. Not as extreme as last summer, but still it is warmer, and it's actually showing a tendency of getting warmer and warmer in every new forecast. No reason for showing you this, it's just the latest forecast. Well, we still have some dryness in the April forecast. But now comes the clue of the story if you change this slide. To get the starting point right, we had, this is taken from another provider showing a hydro balance, meaning if you add up the amount of hydropower you can get from snow, it's an estimate, but from snow, the amount of hydropower you can get from the reservoirs, how much do we then have compared to normal? And this is taken from the French hydrological balance, and it was set to by this provider, but it was a good estimate, around 10 terawatt hours of energy. That's pretty dry. So that meant that the market had a situation 1st of April where there was a risk of this, not an extreme scenario like last year, but almost. If you click again, there will be a new graph, and if you click until the next purple one comes up here, that one, yes, you will see that during April, this is forecast made for every week. So 1 week in advance, and then almost, well, it's a week ago, I think I took that one. What you see happened is that the line here, that is the amount of water coming in, didn't really change, but the short-term forecast actually got more and more wet. And the reality, the amount of water that came in to the Alps, the measurements of the snow, the amount of water in the reservoirs, it actually got up and up and up. And before you click, I'll explain what the next thing is. And the next thing is where I'm verified as a meteorologist in the trading business. It's actually not so much about if I'm right or wrong. It's not about, it's actually not if I'm right or wrong. What I'm measured about is this one. If you click that one, that is the prices of what's going on. I mean, it doesn't matter whether I'm right or wrong. If I can't forecast something that's relevant for the price, I'm not working. So this is my kind of, okay, did I do it right or did I do it wrong? To explain what you're seeing here, I'll start on the yellow line. That's Q1 24. That means the first quarter of the year, next year, 2024. And it is the power price. I just took this one for Germany. So that's actually the average pricing on all hours from 1st of January till end of March next. So what's the average price level then? What's interesting is actually just that it is a pretty flat line. It has a slight decline from 100 and what's this? 155 down to 153, something like that. But it's almost unchanged during this period, which is 1.5 months. Sorry, it's 30 days, but that doesn't matter. It's almost unchanged. The green line is Q4 for this year. So that would be the first part of the winter. And you can see, well, the winter is more expensive than the ones below. So the winter period is obviously more expensive. But the reason for me to show you this, or by the way, this is Q2, so this is also in 2024. I took these 3 lines to show you that looking at winter time and next year, the price level is almost unchanged. However, the red line here, that is the price level for July, August, September this year. And as you can see, that price, the spikes are just data error, so don't look at those. But that price has actually been driving down almost 20 euros. And now I'm generalizing a little bit because, of course, there's a lot of other stuff happening in the environment. But I would say that this is primarily due to the risk of dryness in the Alps being reduced over these 30 days. So actually, we didn't have in this period a new EC seasonal forecast. Yes, there was one coming in here, I know that. But during the period where the prices came down, well, we didn't have any new forecast. We didn't have any news whatsoever about what was happening in the Alps during the summer. But the reality beforehand, before we came to the summer, actually changed the market. So that's, in my world, how seasonal forecasting and sub-seasonal forecasting are connected. Even though nothing new happened, well, the reality came and changed the market. Does it make sense? Yes. If you click again. Many of you have probably seen this one. It is just copied in right in from the ECMWF graphs over the pencil. So I would like just to mention the 2 types of change that could interest me when I talk to my traders. Let's start with what is happening right now. We saw a forecast 1st of January from the EC, and it said that we were going from La Nina to a El Nino situation. And that forecast has pretty much not changed over the next 5 forecast months. It has gone from ending up at around +1 to +2. So that's kind of you could either call it confirmed signal or a more strong El Nino, but it's a gradual change. And that is what many people typically expect from the forecasting models that they would do. Where it gets really interesting is when something happens surprisingly or abruptly or whatever we would call it. We had last year pretty much the same graph, slightly different level, but 1st of January last year, we had a forecast saying we will turn from La Nina to neutral. And actually my expectation was that we would see this development. So I talked to my traders and I said, yeah, we are going to an El Nino situation next winter. February, neutral or El Nino. So we are kind of confident of that. In March, the story was, well, it didn't really confirm as El Nino. It is still confirming as a neutral situation. But yeah, that's kind of the signal as we see about this graph. Even though it doesn't look like much has changed, that was a game changer. Because that was the first sign of La Nina coming in instead of El Nino. And that changed our perspective on the coming winter, the winter we just passed, quite a lot. Because even though I know that statistically there's no difference, then we see the model's behavior being quite different in La Nina situations than in El Nino. Next slide. This is a list, short list just from my head. What would I like to see when I hear about new stuff coming from seasonal forecast? And I took the liberty to take this one, which is from the sub-seasonal forecast of ECMWF. You probably have seen these charts, different types of charts, but I took this in because I really love these thoughts about the regimes and understanding what the weather model is doing. To me, it's great to have all of the statistics on how good is this forecast, but I'd actually like to understand it. I'd like to understand what is it doing. So if I have information like that on the sub-seasonal forecast, I would like to have that on the seasonal forecast. It may not just be the 4 regimes that's usually shown here. There could be other regimes. It's just an example of what I would like to know more about. What is the typical flow into, in my case, Europe? What's the typical, well, that could be something on the polar vortex. That could be a lot of stuff, additional information that I would like to know about what the seasonal models are doing. So I would like to see that. I can't see it like, yeah, I included some other stuff that I would like to see as well. But just to mention that from my perspective, it's not just the statistics I'd like to see. I'd like to see what the weather model is actually showing us in the type of weather, for instance, for each. I think that's it. Yes, any questions? Questions? Yes.
Of the IEA last year, I think it was now year, but when the forecast changed, did that have an effect on the? Could you see a change in prices in the energy market for the winter?
To be honest, I changed my view on the coming winter completely. But I could not see that it had any impact. And I was quite happy about that because that meant that I actually had an edge. And then I think I wrote it somewhere. My work is not about making everybody smart. It's about making my people smarter and hopefully a little bit smarter than the rest of the world. So I was actually quite happy to see that, okay, I changed my view now. I have, I think, a good reason, and I was right. So that actually gave me an edge. But I think that our community as such would be, well, it would be helpful for everybody to know about what the models are doing actually. And then again, finding an edge, well, the more information, the more edges you can kind of find of these things. So I think it's, I hate the word, but it's a win-win for everybody that we have more information to base our focus.
Yeah. So basically, the wish list is more information about why, right?
Yes.
So you get the answer in the seasonal forecast, but you want to understand why, what's driving it. Now, how does that enter into your value proposition? And what does that allow you to do? If you know the why does it have more value than if you don't know the why?
It means that I understand the different scenarios. So it means that instead of just saying this summer will have an average temperature per month of 1.8 degrees more in whatever country. That's of course interesting, but it's not really what the traders would like to know. They would like to know what is the risk of the heat wave like we had last year, or what is the risk of a cold spell coming the coming winter, and how long will that cold spell last? And of course, I can't give them a precise answer, but understanding what the weather model is doing, I might be able to say, well, let's take the cold of last year. We had a December in most of Europe where the 1st of December, the winter came. And perhaps if you look at this statistically now, in Europe, December verifies as slightly warmer than normal. But from 1st of December to the 9th, 10th of December, everybody knew that December would be cold and much colder than normal. All forecasts said it would last more or less. At least the first 10 days would be very cold and the rest of December would stay cold. So what I could say in the La Nina case was that we would have cases like that, where we would have 1 or 2 weeks with quite cold conditions. We would have models saying it would be cold. The market would be high, but it probably would not end up like that when we looked at it afterwards. So it makes it possible for me to put up a scenario to show what the model behavior would be like, because I understand what kind of weather type it is in. Does that make sense?
Ask, I guess, follow up to John's question. So I have to talk to people about what you do. I simplified it to say the most important piece of weather or climate information in the market is the most recent piece of information. And so it's always the most, and the key then is how has it changed from the last piece of information.
Yeah.
And so is it correct that what you're asking for is like you look at the change and you want to explain the change. And then if there's elements that you can't explain, that's where the risk lies. Is that correct?
You can put it like that, yes. Yeah. You can also say it in another way. All of this average, looking at 50 ensembles and the average, the distribution of where we are, it's fine, it's good information, but I'd like to know a little bit more about the individual scenarios and why are they there. We all know that the 50 ensemble that's extreme in some way, probably not going to happen. But if there are 5 ensembles all showing that we will have a cold spell or a polar vortex split, something interesting, there might be some value in these 5 that are not possible to see in just an average.
Sounds to me like that's more of the seasonal forecasting comes in, and there's a lot of presenters there today talking about using machine learning for that. Having some machine learning explainability on top of that to say feature importances of these ensembles contributed this much to the forecast would be one of the things to look at.
Yes, actually, if we go into machine learning language, knowing which feature is interesting is much more important than improving some average by point something degrees.
Yeah.
So yes, feature importance. That's I think. Yes. Thank you.
Thank you.
Yes. And then we'll prepare for the invite.
Yeah,
I think I found more. Yeah.
Okay, cool.
Yeah, just done it.
That was fine. There's no one.
No, Josh, yes.
No, I don't think he gave it.
Okay.
He signed it.
It's here in there.
Yeah, no.
Yes.
Okay, yeah, then, is that coffee break time or is that?
When we introduce the things.
Yeah.
They want a coffee break, but they won't address them.
Yes.
That's one more question here that I found. There was one more question here in the chat that just came in. How often do you make discrete calls? Would you describe your process of making discrete calls a process of art or science or something in between?
Then I will get close to the microphone. So The question is, discrete cause would be what's actually going to happen and whether that is. Yeah. When people who don't know anything about weather describe what I'm doing, I like to describe it as pattern recognition. You could call it art or whatever, but I have to admit that a lot of it is based on my previous experience. And I also know that since I didn't live 100 years, I might actually miss a lot of stuff. So it is a mixture of trying to be a little bit scientific, but a lot of it is kind of the sense of what is happening. So I guess a mix would be the right answer. Thanks. So we are going to have an open space discussion after the break. So I'm going to introduce what we're going to do. Then we'll have the break and we'll set up while the break is going on. Then we'll come back and we'll go through the open space discussion, and then we'll have the wrap up of the workshop. So I have some slides here. So this is open space discussion of energy applications for S2S forecasts. So the way this works is we have 4 groups in this case. We're going to do the quarters in a room, and we'll have a sheet of paper or some post-it notes, and we'll put up all the ideas that are brought out within the different topic areas. So you can change groups, so you can walk around the room, the 4 groups. If you're in one discussion for a while and you want to walk over to the other, so I encourage everyone to walk around. We'll have 4 centers. So Carolina, Helmut, Gregor, and I, each of us will be at one of them. But we'll be the leaders that will be organizing the information that's coming in, right? And so you can change group whenever you think you have said what you wanted, or you are no longer motivated by the discussion. Move over to the other corner, to the back of the room. So you can contribute on any discussion, on any of the 4 topics. And then we'll stop after 60 minutes. So we'll come back after the break. We'll have a 60-minute period. And then after that, we'll have the leaders come back and give a summary of what was said in each of the 4 groups. So the main points. So whenever you come into a discussion, it is okay. So you don't have to wait for any point, right? You just wander in and the discussion's ongoing, and you can get the flavor of it and contribute to it. You can bring up a new topic, maybe it hasn't been brought up in that group before, right? Or continue something that already is in progress, right? And no matter who and what is discussed, it's good. So you don't like the discussion, move on to another one, right? So let's see here. We're not moving. We're not moving. Oh, there we go. All right. So here are the 4 topics. Number 1, evaluation performance. And here are some example questions that might be addressed. And this is by no means constraining, right? We're open to any thoughts of any of these areas. So evaluation performance, things like which performance metrics are most relevant to providers, users, researchers. And imagine there's probably an argument that there should be different metrics for different purposes. So that might be one point to discuss. Are there important issues in how performance is measured from whose point of view? How can the current state of the art performance be characterized? So that's a question that you often hear in the abstract.
Well, how good are sub-seasonal and seasonal forecasts? Right? Well, how do you answer that? And obviously, if you look at all the technical details behind it, that's a very complicated question. Now, how do you formulate some answer to the question of how do you characterize what the state of the art is for sub-seasonal or seasonal forecasts, right? And obviously, it depends upon many, many different things, but what can you say about it? Anyway, those are some points that might be discussed. Services and products, what types of products are most widely used right now or requested? So forecast providers or users may have some insight, not only about what they are experiencing, but also what they have heard in the marketplace, right? How can forecast information be most effectively communicated to users? We've heard some discussion about that already. One of the barriers in the use of existing or new forecast products, the S2S types, why don't people apply it to problems, that would seemingly be open to benefit from this type of forecast? I mean, what are the barriers? Complexity, unawareness, what? Application use case. What is the range of current applications, which have benefited the most? We already heard some today, but I'm sure there are many others of different types. So perhaps we can mention some of those and what some of the issues are, and how has the value to the user been measured, and how could it be better measured, right? So that's always a question. I mean, there's forecast performance metrics, and then there's value to the user, and sometimes there are very different things that we're measuring. Well, anyway, what are potential new applications that perhaps haven't been thought about yet or haven't been implemented? Then research priorities, ultimately perhaps that integrates some of the previous topics. What should be done to increase the value to energy application? So is it about forecast performance? Is it about communication? Is it about tailoring the products to the application? So that's a somewhat open-ended thing. It doesn't always revolve around forecast performance, but obviously forecast performance is relevant to that. So another question would be, what are the most promising pathways to improve performance? Is it more data to the NWP models? Is it improvements or targeting in the NWP models? I think we had some discussion in the break about NWP models perhaps not being optimized for the sub-seasonal to seasonal timeframe, especially the ensembles. If you look at, ensembles are constructed mostly on initialization perturbations, and perhaps as you go the longer time scales, boundary conditions become more important, or sea surface temperature, land surface properties. Should we be perturbing those more for that time frame? So the problem is not exactly the same in the NWP sphere for the short-term forecast or medium-term forecast and that S2S timeframe. And should there be more optimization, or are there other pathways? Is it post-processing that we've heard about? The NWP ensemble data and use machine learning of various forms, or in what way is clustering, right? So there's a lot of post-processing ideas that have been mentioned already. Is that the most promising pathway? And if so, what should be done? What should be the priority in those areas? So these are the ideas, right? Just to get you thinking. So we'll have, I don't know. Oh, yeah, that wasn't good. There we are. So we'll have 4 corners. So evaluation performance will be the left front over there. Services and products here. Applications in the left rear. The left being facing the screen here, and the right rear would be research priorities. Right? So I think we'll probably be a little bit ahead. Well, not so much. So we'll come back at 3:30. Right, and we'll have about 45 minutes, okay, for the discussion. A little longer if people feel there's more to say. And then we'll come back, and each of the group leaders will present a summary of the discussion in each of the 4 topic areas. So we'll take a break and we'll come back at 3:30.
Some of you, the speakers, I tricked thinking the watch was working. You were behind the scenes, especially.
What was I doing there? Were you doing that? What was going on?
Lastly, this one only works with my PowerPoint. You have to focus it while I.
We'll have the leaders give a summary of the discussion. So, Carly, why don't you start? I'm going to Gregor and Helen after that, and I'll finish up.
Okay, well, we were group one, but we talked about evaluation of performance. We talked about other things too, so I'll just report out on what we talked about. For example, yeah, let's start with the last topic. We talked about ensembles. How do you actually deal with outlier ensembles? How do you factor that into your decision? It's important to know under what meteorological conditions, for example, the ensemble is not reliable. That's important information. If ensemble spread is not showing the possible outcome, that could be that all the ensembles show one thing, but reality actually goes another way. That has an impact on trading, for example. Okay, ensembles. We talked about correct and wrong forecast. There was one talk about the beginning of, do I fall into the correct or wrong forecast, but it's also important how wrong was I actually. Talked about seasonal metrics. So the behavior of the model or the forecast can be dependent on what the seasons were forecasting for or when the forecast was initiated, and that could be improved by machine learning. We talked about demand destruction. So you have a forecast and you can factor in price into the forecast, for example, but you also factor in the demand. So let's say something's forecasted to be cold, and then people think there's going to be more demand, but then prices will go up, which in turn will decrease the demand again. So factor all this into the forecast. And how do you evaluate this on a forecast like this? We talked about the evaluation, which should be tailored to the user. Depends on, case wants to know about whether it's all right. We talked about a forecast that about a small risk and a big impact. So there's events that have a small risk and big impact. Those are the ones that are really interesting. And it's also good to know about big changes in the forecasts. If there's something big coming up, then there's a big change because the market reacts to the forecast. We talked about what forecasts have faster trends. So it depends on when the forecast comes in, and some forecasts might be an hour later than the previous forecast that you got from some other provider, or a few seconds later, and it depends which forecast you want. Depends on your scope. So, for example, a seasonal forecast can come in the next day and still be valuable. So the time range is different. Sometimes it's about seconds or hours. It matters which forecast comes in faster. Talk about the human being. So human decisions of what the inputs to forecast are very important. We talked about the increase of ensembles that's coming up and the increased resolution. And so basically the operational model and the ensembles in this future setup won't be, they will have a similar resolution, and so that will change the evaluation of forecasts going forward. And my last note is about measuring skill depending on the atmospheric state, not just like average over a range of conditions, but splitting it. That's it.
Okay, sorry.
We were here in the applications, and we found the very clear ones that we're doing and that we already heard about the last 1.5 days. Specific forecast for each energy sector: wind, hydro, solar, nuclear, preferred, coal, gas, demand, but also transport in the longer run. We're seeing more and more electric vehicles with some impact on the power system. Hydrogen production is a bit of a longer term topic, but will certainly have some impact. And then that's the specific forecast for all the individual energies, but we also need to take the correlations and extremes of those combined productions and demands into account. For the power trading, obviously, we need price forecasts and net demand forecasts, whatever comes first. Then there might be a role for in the there is a role in seasonal forecasts for assessing the resilience of the power system. In Denmark, we had a recent discussion triggered by some reports in the media about Russian activities on the seabed before Nord Stream 2, and that they actually, the same ships that allegedly did that or helped doing that were mapping out cables to UK offshore plants and other North Sea offshore plants. Obviously, remote meteorological events, the more you're having a system that's running on renewable energy, the more you're going to have to transport power over large distances. So remote meteorological events might actually have some influence that they didn't have before. Dunkelflaute being one of the cases here. Then you need a reserve estimation, checking whether you actually need to bring in some extra reserves in the future over the next few months, especially in these cases where you have cable failures. And eventually that can even get to predicting blackouts, which is very simple. If you don't have enough reserve, then the result is going to be a blackout. There's also predicting predictability that might actually have some interesting applications, but I'm not totally sure whether that's seasonal forecasts that we need here or more general weather forecasts or hindcasts or reanalysis products or whatever it exactly is that we need here. And also sensitivities and energy system models, which we also need to address and have a possibility to address. And then there's one idea that came up, but I'm donating that to the services area. And that is ChatGPT for Copernicus. Essentially trying to make sense out of this humongous amount of data with a relatively simple user interface. And people who have used ChatGPT know that it actually can make sense of a lot of stuff. And unfortunately, some of that is useful, some of that is not, and some of that is right, and some of that is not. That's where the receiving end comes in. But there might be some potential in actually doing that.
These are priorities, and the first thing which came up, which I thought was quite interesting, talking about observations, quality of observations. I mean, research is then always thinking of verification. You do something and then you want to test this, compare it with reality. So it's important that you know what the reality is and that you can trust your observation, that it's good quality data. So that's it's very important that we have good quality data. And then thinking now of wind more, it's there's not much data with 100 meters or so. So that's nickel or solar data. Going back historically, that's also not so much. So that's important observations. Therefore, solar is also sky camera would be a useful tool then in the future to help find out what's reality and how, so in the end, how the model is performed. A question which came up, not clear, is there maybe more skill in extremes if ingoing data has higher temporal resolution? So, not just only 6-hour data, but if we have hourly data or so, and then so you have a higher chance of picking an extreme. So, and is that so? Can you trust these also? Another thing which came up, which you already mentioned here, which you started out, is combined combined energy resources. So combined wind, solar, hydro forecasts. How not just forecast for one spectrum, but all together. How does this perform? And the other combination is combine multi-models. It's not clear how to do this. The first presentations combine different models, but yeah, done differently, different people, and so there's obviously not clear how to do this best. There's still research needed. Another question which came up already here was, instead of looking at the weather, looking at the energy, the power, or then the money. I wrote down how to go from the precinct to power and money. And David also said, thinking of clusters, you mentioned it, and Gillian said the choice what you look at, the traders want to look at, like to look at clusters, what other regimes. So the question is, what about not clustering according to weather regimes, but clustering according to power regimes? Could be different, could be better, but then maybe you lose also the relation to weather regimes. So maybe it's less predictive. In the end, it's what you want, but maybe you has less relation to weather, so you might lose also. So that's also interesting questions which could be followed up. That's
I have a comment to one of the things you said, and that's about the extremes and higher temporal resolution. What we've seen here in these talks was that the typical way to do that is to find some sort of a weather pattern, and then find some analogs from a higher resolution model. The research question here is, are there any weather models or weather types in the future that we don't really have enough data for?
The answer is yes. Marine heat waves is a great example. There's almost no analogs for existing marine heat waves. And it's a forecasting problem.
Yeah, is that the circulation that's in it, or is that just the
It's the sea surface potential anomalies and where you don't find analogous. Like you go back and find El Ninos and La Ninas, but 3 degrees Celsius anomaly off the west coast of New Zealand. And it has happened in recorded history.
Okay, so the last group here was services and products, and we're dominated by forecast providers and users. So the perspective we got might not be broadly representative, but it's interesting that although the apparent trend in society is for intelligent systems, AI and machine learning approaches to synthesize data and give you an answer that you can use for decision making. The discussion here was that the trend among users, and we heard this both from forecast providers and the users, was that they want more information, not less. So they want to see all the components of the forecast. They want to understand what factors modulate forecast error. And they want things like a time series that might go out in hourly increments for a year. And you might say, well, why would you want an hourly time series for a year when after 7 days or so, it probably has no still as an hourly time series? But it was a flexibility issue because it allows you to compute statistics of some future month, right, or a season where you might be able to look at a distribution of variables, right? So when it comes from an MWP ensemble, there might be information there, not in the individual hourly values, but more than the mean. So, and you just had a forecast and a mean for the month, right? That wouldn't be equivalent, perhaps, and it has to be some research done as to how much information there actually is in the statistics of the time series. But again, it's in that flavor that the user wants to know more about the forecast, not just the final answer, right? And so that opens up a number of issues, right? That, well, you can misuse the forecast if the user, for example, believes the hourly time series values actually have some predictive value, right? That wouldn't be good because there probably is no value there. So it requires a lot of education as to what might be useful in these additional data sets and what probably is noise, right? So that's a big issue that we discussed, that there needs to be education and understanding on the part of the user if they have more information, because I think it was commented that the provider, that what we do is really hard and the user wouldn't want to do it, right? So the provider is doing a lot of work. And I think in different ways, most providers are, and they're giving you a final answer. And then the user saying, okay, that's nice, but I want to know all the factors that went into that final answer. And there was a bit of a debate as to why should you know that, right? That if you have a reliable final answer, right, that in theory you can't improve upon, you optimized it with the information you have, what is the value of all this other information that is really components that went into the final forecast? But yet there was a comfort level, or it was pointed out that there might be an ability to customize the forecast by the user. So although the provider is giving the user a forecast, presumably what the user requested, but yet there was some thought that there would be ability by the user, because they understand their problem probably better than the provider, or at least they feel they do, and therefore they want to have the data in order to possibly customize it further, right? And along that line, it was brought up that standardization is a very important issue. That if you're going to get all these different data sets, that the data formats, right, the file formats, the variables, the resolution, the time increments or time resolution, all that varies. So if you go to different models, different sources, you get a wide range of all these different factors that are not standardized. And that makes it difficult for a user to use multiple products. And some providers take some subset of information, try to standardize it, and we'll give it to you. But it would be good if there was a standard for many of these things, in terms of data formats, resolution, and so forth, so that different data sets, different forecasts can be compared, right? And another point that was made was that AI is difficult to apply to long-range forecasts because of the sample size, right? That especially for a large amplitude anomalous events where you don't get many of them, right? So can you really expect some type of procedure that is trained on a data set that may have one event over a 20 or 30-year period, right? To really reflect accurately, the possibility of that event. I mean, that was an open question. That's probably a research question. How do you get reliable information about very large, rare anomalies, or even in the case of climate change, unprecedented anomalies, right? That may not happen often, it may never have happened before in that magnitude. So I think that was it. A summary of what we've talked about. So I think we're done. Gregor, you have some final comments to make about where this is going?
No, but I can.
Okay, I mean, we are going to do the paper, right? Do you want me to mention that, or?
There's, there should be, the final outcome of this should be a paper of sorts. I hope that someone else is taking the lead on that one, because I'm notoriously not good at getting this done. Other than that, tomorrow is going to be a task meeting, and some of you are on the trips to Wokingham to the control room, and some in the morning while we have the task meeting. I sent you a mail saying, please make your way to there by yourself. I know that at least Gorka wanted to take a taxi from his place, so maybe there's more cars that can be shared. In the afternoon, the ones of us who are on the task meeting should be able to get a taxi, or I think, David, you said you had 3 places in your car, and maybe we have one more from Reading who also joins. But we'll figure that out tomorrow. So the task meeting tomorrow is we're having one talk from JUA.ai, which is the company claiming that they have a fully deep learning weather model that runs a 48-hour forecast 1 by 1 kilometer globally in 15 seconds. And I thought it might be a good opportunity to throw them before the meteorologists here. to get to know what they're actually doing, and then we're talking a bit about the different work streams, but not that many, and then we're talking about collaboration with the solar task. Then have that visit to Wokingham. Other than that, I'm thanking my hosts, especially Chris, who did all the heavy lifting of the logistics and connections and room booking and everything. And David, of course, for saying yes to Chris doing all the work. Yeah, and you all for coming here. It was a pleasure meeting you. Also the people online, and see you.
One quick thing that people come to working tomorrow, and if you can remember to profile, otherwise everything. Will you send us a link to where we can see the PowerPoints, maybe the recordings?
I will put them on our website, and including the YouTube videos of the entire event.
Just right, I don't know how open or close the task bit of this meeting is. I'm just thinking there might be several people around the partners who do AI, duo AI is that an open thing? Can I get around the emails here? Jim, if you want to do it, department to 10.
Go ahead.
Okay.
Any feedback on it? I'll be there, but I really like to.
I don't know. Who knows? I imagine there was some comments from someone.
I assume it's a virtual talk. Are they joining on Zoom?
No, they're actually in London.
Oh, okay.
So they promised to be here in person. 9 o'clock.
9 o'clock tomorrow morning.
Yeah.
So it's at 90, program says 20. So if I'm interested, if I'm emailing around it, it's not happening.
Yeah, okay, I'm probably saying I'm saying a few words administratively about the task before that, but 9-ish. Quarter past, 10 past, 20 past. Ish, exactly. Yeah, and then the next events of the task is going to be some very likely some online meeting in winter, and the next planned workshop is going to be on the exact other end of the horizon scale, minute scale forecasting, together with task 44 on wind farm flow control, with task 52, I think their name is now, on LiDARs, with Jan Riemund and his people from the solar task, and maybe some other people who are also interested in that. But that we are planning for next summer, or spring, summer, and we have to figure out the details of that. Good. And with that, I'm closing this meeting.